So I think let's start as we cannot wait any longer, and people will be joining. So my name is Martin Gordon Mubanjizi, a data scientist and also acting head of Pulse Lab Kampala. And I'm going to be moderating this morning session with Joyce Nabende, who is a senior lecturer at Makerere University, but also the head of the AI lab, of the AI and Data Science Lab at Makerere. For social media lovers, Data Science Africa has a Twitter handle. Make sure you follow, because I was told you may get some information for a lunch coupon to the nearest restaurant in your area. Our program this morning will begin with welcome remarks from Billy, who is the program chair, and also Joyce, who is has been the general chair for this event. And then thereafter we shall be introducing different sessions. So I would like to call upon Billy and Joyce, to give us their opening remarks. Thank you. Billy, over to you, and Joyce.
Thank you, Martin, for the warm welcoming remarks that you have given. I'll probably let Billy say a few words, and then I'll try to go through this presentation.
Okay. Good morning, everyone, or good evening from those of us who are in evening time zones. Welcome everyone to another edition of DSA, Data Science Africa Summer School and Workshop following up to this. It's unfortunate that we don't get to meet in person as we would have hoped in the beautiful Makerere campus in Kampala. But nevertheless, we can't let COVID keep us down. We are striving on to keep doing the good work of data science and using data science tools to solve real practical problems. So this morning, we've just prepared a brief slide set to show you a little bit about Data Science Africa, a little bit about those who are here, so the participants, where they're tuning in from, just to get a sense of the connectedness, and then a small overview of the program, and then we'll jump right into it. Joyce, back to you.
Thank you, Billy. Good morning, everyone. Good evening, everyone who's managed to join us for this first session of Data Science Africa 2020. So what's DSA? For those who do not know, especially the fact that we have very many first-time attendees, which is very exciting. The first DSA event that we've had in 2015 in Kenya, we've had several summer schools and workshop sessions every year. And for most years, we've had 2 events running concurrently, not concurrently, one after the other. Each year, as we've been trying to host a DSA physically. What is Data Science Africa about? We are focused on end-to-end solutions that are practical and relevant to the challenges that we face in Africa. And we've had very many success stories, very many labs, startups coming up. And we'll have a big announcement later on about research grants that DSA is also posting. So this is very exciting, and we're moving in a good direction. DSA is a non-profit organization that's managed by a committee, board members, and advisors. So this year we had hoped that you'd all come and visit our beautiful campus in Makerere University, but unfortunately, because of the circumstances we all know, we've not been able to have that, and that's why we are virtually here. So just to give you an idea of what Makerere University looks like from there, and hopefully one day we'll still have it back in Kampala. So we'll try to make the most of the situation, and that's why we have this webinar format. And as DSA, we've attempted to already have a webinar when we had our COVID webinar some time ago. Sorry about that. Yes, you can. Sorry about that, working from home. Yeah, so we had our COVID webinar some time ago. It was very successful. And so we thought we'd build on that success to also have the DSA that we have today. So in terms of the statistics, it's really exciting to present this slide one because based on the participation, we've had over 36% of the participants are coming from Uganda. But on a good side also is that we've had very many countries are being presented as part of this virtual DSA. So to all the Ugandans on the call, please clap for yourselves. We've done remarkably well to be part of this virtual DSA. That was exciting, but the bad thing is that the males are still more dominant than the females because we only have had a representation of just 22.3% females, while 77% are males. So I believe that we are getting there as females, but we need to do much better in terms of our representation. In terms of attendees, we have lots of first-time attendees. Over 84% of the people are new. They've never attended DSA before, which is also very exciting for us as people preparing this. Then most of the people on the virtual DSA are students compared to the people who are not students. But also I think it's good to note that when we are doing DSA, we're not only focusing just on academia, we also want to bridge this with the people who are in industry such that they can be able to take the skills of machine learning and data science to use even when they're out there in industry. So I think this is a very good representation that we try to merge both aspects, academia and industry, as we try to have these workshop and summer schools. In terms of the educational profile, I think we're targeting the right group because bachelor's degree is really good. They're very enthusiastic at that stage, and we have many of them here, and spanning into this data science and machine learning program. So this is very good to have a very great representation of the bachelor's degree at this stage during this DSA workshop. So just to see a word cloud showing us how did people hear about DSA. So as you can imagine, because it's really been virtual and because of the circumstances that we've had, it's really been around Twitter, social media, Google. But it's also good to hear that there are people part of the DSA board whose names are actually here, like Dina, like Neil, like Eric. So thank you guys for spreading the word round for DSA and having such a great participation that we are having currently on our DSA platform right now. So this is where people got to hear about DSA, and it's very, very exciting. Yeah, so we would also like to appreciate our sponsors, Facebook and who have made this possible, and all the universities, Makerere, Nelson Mandela, Denan Kimathi, Makerere AI Lab, Pulse Lab Kampala. These have really played a great job in supporting us and ensuring that we don't give up because we're not able to meet physically, but that we could still have this space where we could be able to meet together and have DSA. Yes, thank you very much. Over to you, Martin.
Thank you, Joyce, for that wonderful presentation. I never expected the details, and it's such interesting, the composition of the participants, and you really you were able to to explain it well. So we I think we shall now dive into our first presentation by Claire and Neema, Introduction to Python and Jupyter Environment. So Claire, I can see Claire. Claire, could you share your presentation?
Hello?
Hello.
Okay, I guess you can hear me. Do I have to switch mode to the other link for the presenters, or this will work?
You try sharing your screen and see.
Okay.
Okay, so it works.
Okay. Well, I don't know if I have to go to video for a minute for people to see me.
Yeah, that would be good.
Yeah, okay, let me do that in a minute.
Okay.
Okay, I cannot start the video. That's what it says.
Okay. Okay, you can start presenting. Let me check what the problem could be.
Okay, good. Hi, everyone. I will not say good morning because we have quite a number of people who are coming from different countries in different time zones. So, hi, everyone. I'm glad to be here on this virtual data science conference, Kampala. My name is Claire Babirye. I work as a lecturer at Uganda Technology and Management University, UTAMU. And I also work as a research assistant in the AI lab at Makerere University. So my co-presenter, in her absentia, she's called Neema Mduma from Nelson Mandela International University. So she came up with this presentation, and I think I'm going to leave it going for a while, and then I'll come in later and present. Yeah. Okay. So can you hear the presentation? Okay.
You can see the presentation. And you can now, I think,
Are you hearing
now...
anything? Okay, so there is a sound to the presentation. Are you hearing anything?
No, we can't hear anything.
Okay, just a minute.
Hello everyone, my name is Neema Mduma from the Nelson Mandela African Institution of Science and Technology. I'll give a talk on Python, pandas, and Jupyter tutorial, and my friend Claire will take you through the practical session. So what is Python? Many people have something in their mind when they hear the word Python. But today we are going to discuss Python in the aspect of data science. Python is simple, easy to learn, powerful, high-level, and very popular general-purpose programming language. It is open-source general-purpose language. It is dynamically semantic rather than statically typed like Java or C or C++. It is also uninterpreted rather than compiled like Java or C or C++. Generally, Python is easy to learn and use. It is a developer-friendly and high-level programming language. Python language is more expressive, means it can easily understandable and readable. Python is an interpreted language, meaning interpreter executes the code line by line at a time. This makes debugging easy and thus suitable for the beginners. It's a cross-platform language, means Python can run equally on different platforms such as Windows, Linux, Mac, and others. So we can say that Python is a portable language. Python language is freely available in the source. There are There are several applications of Python, starting with web development, using different platforms such as Django, or Flask. In web scraping, when you extract large amount of data from the website using platforms such as Beautiful Soap. Python can also be used as a scripting language, as a scientific programming and numeric computing, in automation and embedded system, and as a desktop graphical user interfaces and 3D modeling. The importance of this language is that it can be used as a teaching language due to its simplicity and user-friendliness. Python is not intended to work on a special area. That's why it is known as multi-purpose, because it can be used in different web application or enterprise and so many others. There are several versions of Python, and currently we're in version 3.8.3, which was released on May 2020. These versions come with updates based on the user and system requirements. Python has so many packages. Just to mention a few: Jupyter, NumPy, SciPy, Pandas, Matplotlib, and Scilab. The selection of these packages will be based on the purpose which you want to achieve. We are going to discuss NumPy is a fundamental Python package for scientific computing. It covers the high-performance vector, matrix, and higher dimensional data structures. SciPy is a package that's based on the collection of high-level mathematical operations, such as linear algebra, optimization, integration, differentiation, and so many others. Think of the scenario where you want to focus on visualization. You can use Matplotlib, which is an excellent 2D and 3D graphics library for generating scientific figures. It provides both a very quick way to visualize data from Python and publication quality figures in many formats. We have other data visualization packages such as Seaborn and Bokeh. Pandas is a Python package providing a fast, flexible, and expressive data structures for data analysis. It's a fundamental high-level building block for doing practical real-world data analysis in Python. And it was designed to work with both labeled and unlabeled datasets. Thank you very much. I hope you enjoyed this session. Now we are going to welcome Claire to proceed with the practical session.
Okay, so in brief, that is it about Python. So we've learned that it's a language that can be interpreted, and it has been used for quite a number of things, from teaching to developing different applications. And now we're going to go through the practical session. Just a minute as I share my screen. Okay, so in the practical session, we are basically going to look at, we're going to go through a Python crash course, and then we are also going to go through one of the packages which has been highlighted from the theory, and that is pandas. But maybe since the crash course has been fully developed for us, we're going to first go through the pandas tutorial, and when time allows, we shall come back to the Python crash course. Okay. Yes. So I'm hoping everyone already has the environment which we are using, and that is Anaconda, because if you have Anaconda, it already has these different dependencies for Python, and so you'll be able to follow along. Yes. Okay, so pandas is basically a package that is used for data analysis. So you can look at it as Excel, and by data analysis, we basically mean that if at all you sort of like have some form of data, and this data has quite a number of features, okay? Can you be able to analyze the data, and then you generate insights from the data, you generate patterns from the data, and so on and so forth. So pandas supports data analysis, but as we go deeper in the summer school, you will see that basically when we talk about data analysis, we have what we call exploratory analysis of data, and then we also have what we call the predictive analysis. So for now, for this tutorial, we're going to focus on exploratory analysis. So think of it as descriptive analysis. And we are going to look at a case study, and we shall sort of like try to analyze the data that we have in the case study and see how can pandas help us to generate insights from this data. Okay, so these are the few basic concepts that we're going to look at, and that is creating data. So we are going to look at a scenario whereby we create data on our own, and that can come in, for example, if we think of a case scenario and then we present it in such a way that we input this data, maybe in form of lists or in form of dictionary, and then later convert it into a series, and then finally into a data frame, okay? Then we shall also look at another case where we deal with already existing data. And for this particular example, we are going to only work with CSV. But as you do research moving forward, you'll find that we can also have data input in from different files. For example, JSON, it could be a URL, it could be a database, and so many others. And then we shall also go ahead and look at some of the different methods that pandas has, which basically help us to manipulate this data, to explore this data. And then later we shall have an exercise for ourselves. So, okay, so as I said, if you have Anaconda, it means you already have pandas installed within the package, within the entire package of Anaconda. So what you do basically is you just import it like the way you see here, import pandas. And then the reason why we are importing it as PD is because every time we would want to refer to it, we would want to use PD instead of using the entire name pandas. And then after importing it from that particular package pandas, we can import the data frame and series. Now, we're going to look at data frame and series. So the difference between data frame and series is that basically a series is sort of like a holder that can hold data in a one dimension. So for example, if we look at the example below here where we create our own data, and in this case we create two lists. One list is for the names, and then the other list is for the weights, okay? So later on, when we come to use this data that we've stored in a list, you can see that we now take the list and then we translate it into a series. And at the end of the day, when we sort of like look at the series, this is basically what we have, something like this. So a series is basically a one-dimensional array, or it's not a variable, but it's a holder that can help us to hold data in one dimension. Yes, unlike a data frame. So a data frame, for it basically helps us to hold data that is more than of one dimension. So for example, if I have more information about these different people, then that means that it ceases to be a series, but rather it's sort of like a data, it goes into a data frame, okay? But now when you look at the contents of the data frame, we shall realize that each column is sort of like a series. Each column in the data frame is sort of like a series, okay? Yes, so here we create our own data. We've created a list called names, and then we've also created another list called weights. So the reason why we are using the quotes here is because the kind of data that we are storing is a string, and so that means it has to appear in quotes. But now here we are storing integers or numbers, and for them they do not need to be in quotes. Okay, so then later we come and store our data in a series. So the data that we are storing in the series, we are picking it from the list which we called names, and we would want to index that list with weight. Okay, so that's why you can see that we have 70, 75, and so on and so forth. Okay, but otherwise, if we sort of like do not specify this, then it will sort of like, so it will sort of like take on, it will take on the default index of 0, 1, 2, and so on and so forth. Okay, something like that. Yes, so we can sort of like be able to retrieve contents from a series using the index number, sort of like indexing. And so if I specify my series called series name, I specify index 70, then it will return whatever is in that index, okay? And as you can see, it's Brexit. Yeah. So that was one version, but this is also sort of like the same version. But here what we do is that we do not create the lists like we did earlier on, and then come and use the variable name for the list. So here we do it directly, or we did it directly, and that means that we went ahead and added the list here. So you can see we have our different names here, Damali, Damon, and so on and so forth. And then we also went ahead to specify the index. So in that order of indexing, so each index will sort of like map to a name, A for Damali, B for Damon, and so on and so forth. So still we can be able to retrieve the data from the series, okay? So that was one version of creating series from lists. But the other way is that we can create series from dictionaries. So there is what we call a dictionary. Dictionary, it's basically allows what we call paired values. So we shall sort of like have a key and a value. And as you can see here, we have a key of 0 and the value is Kampala. We have a key of 1 and the value is Arusha, and so on and so forth. So these are sort of like some of the cities that have hosted Data Science Africa. And so we shall have something like this when we call the dictionary as an output. So later, we can now put this information in a series, as you can see what we have here, and so it will return something of this sort. Okay, so it does not differ to what happened when we're picking this information from the lists. Okay, then we also go ahead and created another series that is for population. So we can see that now we are using the same keys. Okay, the values are different, but we are using the same keys. Okay, then finally another series called area per kilometer, still the same keys but different values, something like that. So at the end of the day, we can now sort of like combine these different series to come up with what we call a data frame, a multi-dimension array. And this is something that we come up with. So since we already imported data frame from pandas, then we can sort of like call it here pd.dataframe, and then here we specify that the column name is city, and it's going to hold DSA cities. So there is a dictionary called DSA cities, which had our cities. And then this other column name is size. It will hold information from area per kilometer. Then population will also hold that. Okay, and at the end of the day, we come up with something like this. Yep. So we can query the data. For example, just keep running this. Okay, so we can query, for example, if we do data.city, where data is the name of the data frame and city is the column name. So this basically means that return the elements that are in this column. And so it sort of like returns something of this kind. Okay, so the reason why I'm commenting this out, because I'm running this in the same cell, and so it can only return for the very last, unless when I print out the information above. Then I can also go ahead and find out the columns in the data by printing something like this, print in brackets data.columns. So if you're using a higher version of Python, you have to put whatever you're printing in those quotes, okay? So earlier on here, we're basically now calling information on one column, but alternatively, the other way of how we can do it is we can sort of like say data, cities, something like that. So these two work sort of like in the same way, data.city or name of the data frame .column name, or if I have the name of the data frame in square brackets in quotes, I have the column name. It sort of like works the same way as this, okay? Yeah, but now in case I want to return content on more than one column, then I have to specify all the columns whose content I would want to return, and then I have to double list, okay? Something like that for size and population to be returned. So even if I'm sort of like adding another column, I do not add another pair of a square bracket, okay? So it's double, it's either one bracket like the way we see here, or it's two pair of brackets like the way it is here, okay? And then we can add a new column. For example, if we look at the data frame that we had, so this is the data frame that we had, maybe if we sort of like look at size and population, and we think that given size and given population, we can sort of like generate more information, then we can add a new column. So the column that we added here is called population density, and this is given by population over the size. So the population of that region over the size, and we know that we already have the size in area per kilometer. So we can be able to add a new column. And how we do that? So we just sort of like call the new column that we want. And this means that we think of a column name, okay, and pass it on the data, and then equate it so we equate it to some formula this side, but we have to make sure that whatever is on this other side, we already have it in the data frame. So we already have population and we already have size. This is the only new variable that we have. So at the end of the day, we shall sort of have like city, size, population, and then population density, okay? Something like that. So this is, this means divide. So that is an example where we are creating data on our own, okay? And so on and so forth. Now, let us look at a case where we are dealing with already existing data, okay? So maybe I'll get the questions later. In case there is any question, I'll get to them later on. Let us look at how to deal with already existing data. So I mentioned the fact that pandas can read data, okay, from different formats. So we can have CSV data, we can have Excel data, we can have data that has been fetched from a website, we can have data that has been fetched from a database, and so on and so forth, okay? And now here we have an example of data that was collected on COVID, okay? Whatever is ongoing right now in the entire world. Yeah, so this is data that we collected on COVID from one of the websites. And so how we collected it, basically downloading it, and then it sort of like allows you to save it in a CSV format, okay? So when it comes to dealing with already existing data, the very first thing that we have to do is to read the data into the notebook, okay? So we sort of like have to read the data into the notebook. And this is basically what we are doing using this method, okay? So the methods are also quite many, but depending on that data that you have, then you select a format, okay? You select a method that works for that particular type of data. So since our data is in CSV, this particular method, read_CSV, basically works, okay? So we read the data, and this is the code, and now here we store it in a variable called COVID data. So this means that every time in this notebook we want to refer to this data, we shall just call it by COVID data, something like that. And this is what we do in the next cell. Okay, I hope you can see my interface. So this is what we do in the next cell. Yes, we read it. So you can see it has quite a number of columns. Like I said, now this data is in a data frame, and the data frame sort of like supports a multidimensional. It's a multidimensional array, so it supports data which has more than one attribute or more than one feature. So the data that we collected was up to 1st July, because that is the day when we got this data. So it is up to 1st July 2020, but it starts from the period where that country had the first case. So for example, let's say like China had the first case last year in 2019. So you will see that the data for China stretches back up to 2019, in case you're wondering when did it start recording. Okay, so we have the date represented, then we have the day represented, we have the month, the year, and then we have the cases. So the cases sort of like up to date, and then we also have other deaths that were registered up to that time. We have the countries there, and so on and so forth, and the continents, okay? So when we're now doing our data analysis, our exploratory data analysis, we didn't really consider all the features or all the attributes that are in this data. For example, this one, we didn't consider it, but there are so many things that you can do, okay? As you'll see as you go down. Okay. So now, maybe the first thing that you can think of doing is to do a dot columns, okay, on the name of the data frame, basically to see what attributes do you have in the data. So the beauty is that here we do not really have so many attributes, and that's why you see that maybe when we scroll this side and that side, we can be able to see all the attributes in terms of like the names. But you'll find that there are those huge data sets whereby you have, let's say, up to 54 attributes. And so maybe the representation, actually, a few attributes are sort of like represented, and then there are those dots and then other attributes, okay? So dot columns, this particular code here. So what it does, it helps you to return all the columns, and the columns are what we are calling the features or the attributes of the data. Okay, and like we've seen there, we have the date represented, and these particular elements have been extracted from the date, that is the day, the month, and the year. Then we have cases and so on and so forth. So we can think of a few things, and maybe the first is we can do selection and indexing, okay? So for example, if we sort of like want to return the cases that we had, remember this is daily data, okay? Daily data. So how many cases were there maybe in Uganda on 1st July 2019? How many deaths and so on and so forth. So it's sort of like daily data. But you can see that certain countries had a very high number as I scroll through. And then you can see certain countries didn't have any case on a given day, while others had around 1, around 3, something like that. Okay, yeah. Then still we can be able to return cases and deaths. So all this is selection. Like we mentioned when we are creating our own data, if we are now returning information on more than one attribute, we have to sort of like double use the 2 pairs of square brackets or double list. And so you can sort of see something like this. Yep. So still we have regions where we had death occurring, but then we also have regions which had 0 death on a particular day. Okay. Yeah. So the columns within the data frame are just series, and if you basically want to find out, what you do is that you use this type method on any of the columns on the data, and then you can sort of like be able to find out the type of column that you can have. So this means that this column called cases is a series. Okay. Yep. Yeah, then we can be able to select the rows in the data. So the rows in the data are sort of like our records, and these are sort of like the entries that we are getting every day, okay? So if we use the .log method, okay, which is basically now going to return content in this position, it will return whatever content that we have in position 0, and that is the very first entry that we have in the data set. So it returns something like this, the date, which was 1st July, okay, the day, the month, the year. These were extracted from the very first column. And then the cases, the death, and the country. So this is Afghanistan, which is in Asia. Okay. Yeah. So then another method that we can use is .ilog, which will also help us to return information based on a given position, okay, based on a given labeled position. Okay, so if we sort of like have position 2, then we can be able to also return the content that is under that particular entry. So we can see that this is information that was logged on 29th June, and yeah, 351 cases at the same country, Afghanistan, and so on and so forth, okay? Yeah. Then we can be able to select subset of rows and columns, because now we've selected columns only, we've selected rows only, so can we sort of like be able to select subset of rows and columns? So if we use the .log method and we sort of like query for this, so what this means is that in position 0, return the number of cases that we have in position 0. In other words, in the very first entry in our database, okay? And so it sort of like returns 279, just like we've seen here, okay? That we had 279 cases, yeah. Something like that. Then we can also have another representation here. So now here we are selecting more than one record. So we are selecting whatever is in position 0, whatever is in position 2, whatever is in position 4. What do you return? Return cases, return death, and maybe you can also add something. For example, you can say return countries and the territories. Yeah, so you can see this is information on Afghanistan. So this can also actually give us an idea of how our data is appearing, because it's sort of like country per country. but it's following the alphabetical order, something like that. Yeah, so diving into selection more, we can have what we call conditional selection, okay? And this is an important feature of pandas, which uses the bracket notation, sort of like, yeah. So conditional selection, for example, if we specify a given constraint or a given condition, can we sort of like be able to return information per that particular constraint that we have specified? So for example, if earlier on what we're basically doing, we said that just return the cases that we have in the data, and it sort of like returns something like this, okay, COVID data cases. But what if we want to see something that is more than, let's say, 200, okay? So this means that it's going to return those records. However, it's only going to return cases, okay, whereby the value is more than 200. Yeah. Okay, something like that. But what happens is that this particular segment of code, it returns a Boolean value. And that means that sort of like returns all the records actually that we have in the data, but wherever this condition is met, it will return true, okay? And where the condition is not met, it will return false, or something like that. And so that's, that was this sort of like comment that we had here, that it returns Boolean values. So if we wanted to return the data frame, okay, but following the condition, then we sort of like have to do this, what is, so this is sort of like what we have. So if we wanted to return the data frame, sort of like add this. And then it will return the data frame, okay? So it will return all the information in the data frame, that is the COVID data frame, okay? But it will put a constraint on this column cases, okay? So that's why you can see, if you look through the index, you can see that it's sort of like now not in order, okay? You have 1, 2, we have 3 missing. So basically 3 is missing because it did not meet the constraint and so on and so forth, okay? So it returns the entire data frame. But if at all we want to, if at all we want to return specific columns, okay? So after the constraint, we can go ahead and mention the columns that we would want to return, okay? Something like that. So still, if I have that constraint, so for example, let's say maybe I want us to return only the countries and territories where the cases were above 1,000 on a single day, okay? Then it will return something like this. So you can see we have the United States, we have Bangladesh somewhere, we have Austria, and so on and so forth, okay? But we can return more information. So if we want more information, still we do the double list. So for example, I can say return death. So where we, on a single day where we had cases rise above 1,000, did we sort of like register any death? That's sort of like something like that. And actually, yes, we have these cases here. So we had Afghanistan. Maybe we can also actually return the days themselves, since the data includes the days. So you can see Afghanistan, that was on 16th May. We had cases above 1,000. And on that day, they registered 32 deaths, something like that, okay? Yeah, so you can see United States on 15th April, they had cases above 1,000, but they registered over 2,000 deaths, something like that, okay? So that is conditional selection. Yeah. So now, what if we have more than one condition? Can we sort of like see how to return data? So for example, here, I'm sort of like curious because I want to see that, okay, according to the news, the virus was in China in 2019, according to media. So sort of like curious, from this website, do they have like other countries also having corona in 2019? Yeah, something like that. So I specify the month because we already have a column called month. So I want the month when the month was 12. Okay, and this is sort of like an assignment operator. These are the double equal signs. And then here I'm using a condition called and this means that at the end of the day, whatever information that will be returned will be that where the condition on the left and the condition on the right are both true, okay? Yes, because sort of like the opposite of and is all. I guess we are certain, yeah. So for all, it will return any where the condition is met, but for and, it will return only data where both conditions are met. So now I specify the year as 2019, since we are saying that also the year was extracted for us from this particular column called date rep. And when I return this, I actually get to see other countries, yeah? So I get to see Afghanistan, Algeria, and so on and so forth, right? But media says we had the virus only in China. So, well, when I got to look at the cases, these particular countries actually didn't have any cases, okay? But our source, our URL source, this website where we fetch the data from, it logged regardless of the fact that these countries didn't have the virus then, because you can see the cases are 0, okay? Something like that, yeah. But now maybe we can actually add sort of like another condition, okay? And this would be the third. So we've seen that we have very many countries with these two conditions because of the way in which the data was fetched, okay? Now, what if we add another constraint, and this constraint would be that let us only see information where the cases are greater than 0. In other words, where we registered a case, a COVID case. So when we do that, we actually end up with China as it was in media. So we can see, according to this website, on 31st December 2019, China reported 27 cases, okay? So something like that. So you can see that at the end of the day, you can be able to tell a story from your data, yeah? Another method that we can think about is the group by, okay? Because now we've already interacted with our data and we've seen that we have quite a number of features where we can group, but we've also seen that we are logging data on a daily occasion. So what if we analyze it maybe on a monthly occasion, okay? Something like that. Or what if we look at it on a continent level? Because we can see that each country, at least it belongs to a given continent, yeah? So this can sort of like be achieved using the group by operator, okay? So the group by operator is a method that allows us to group rows of data together, and then we can call aggregate functions. So quite a number of functions, as we shall see, sort of maybe averaging or doing a summation, among others, okay? So for example, if we call the name of the data frame and we apply the method, okay? And you're saying that group by, so group by what? This particular column that is called continent exp, that is holding our continents, okay? So this means that at the end of the day, when we do this, we've sort of like come up with an object, a group by object for this particular column. So we can maybe give it a variable name, and the variable name sort of like that makes sense. So for example, by continent. So that means that if I subject this to a variable name by continent, then I can call my aggregate methods. For example, I can say by continent dot mean, and this means that by continent, find the average cases, find the average death, okay, for the data. So that means that for now, we are not sort of like catering for that time, but we are saying that for the entire data, sort of like average on a continental level. So we can see that we have Africa in representation, we have America, we have Asia, we have Europe, we have Oceania, and then we also have a continent called other. But maybe we shall deal with it at a later case. And so you can see we have something of this sort, that on average, Africa has registered 69 cases, odd, and still on average, we have 1 death. America has 951, 45, and so on and so forth. So you can see actually on average, America really has the highest cases and it really has the highest death. Yes, and it's followed by Europe, then followed by, sorry, it's followed by Asia in terms of cases, but in terms of death, it's followed by Europe. Something like that. But you can see Oceania has like 0.1. So now these are sort of like further discoveries that you can make in the data. So what countries are in Oceania? Sort of like that. Okay, so this is sort of like same as this, but here now we are doing it directly. Instead of creating a variable, or instead of creating a group object, subject it to a variable, here we are saying we sort of like do it at once, okay? At once, we group by this column, find the mean for these particular columns that we have, cases and death. So it does not differ any much from what is above. Then we can also find information on other aggregate functions like the standard deviation. And we can sort of like compute these values. So .std is the method that is invoking our standard deviation formula, okay, that is already embedded in there. And then we can also see the max. So this is sort of like returning the maximum cases. So Africa, the maximum cases that we've had, 7,210. The maximum death is 168. America, 54,771, and so on and so forth, okay? So, yeah, so that's maximum. Then we can also do a summation, okay, per continent. Because remember, we are logging data on a daily occasion. So we can sort of like decide to sum it up, but how the sum up works or how the summation is going to be done is based on continents, okay? So that means Africa is going to get information on all the African countries that we have in the data, then it sort of like sums it up. And then we can see that we've had a summation of up to 405,076 cases here in Africa, yeah? And so on and so forth, okay? Yeah. Then we can also add, we can also do what we call a count. Now summation and count are sort of like different, okay? And you can see this from the values or from the output. So Africa, in terms of summation, we've had 405,076 cases, but in terms of count, we've had 5,851 cases. So count is sort of like, what is count doing basically? It's sort of like incrementing. So it goes into the data, it picks each record, okay, where the continent is Africa, and then it sort of like keeps on incrementing, okay? So that means that in terms of, okay, sort of like you can see the equivalent method here down. So if I sort of like, so if I sort of like get this data, okay, that is COVID, and then I say, what was the name? I think it's continent. Yeah. So I specify Africa. Okay, I want it to return. Okay, so this basically what it does, it returns a data frame where this constraint is meant, and the constraint is the continent should be Africa. So if I do a length, something like that, then I can see the 5,851, okay, which is sort of like equivalent to count here that we have here. So count is basically now getting the cases that were registered under Africa, okay? Yeah, then summation, it's now looking at the value that we have under sum and the value that we have under death, and it's sort of like summing them up, yeah? Then we can also get as much information as possible using the .describe method. For example, you can get cases, we can get the mean, which is the average standard deviation. We can get the minimum. We can get these different percentiles and the maximum and so forth, on and so forth. So you can get it for count, and then you can also get it for death, okay? Yeah. So same thing, but here what we do is we've used the transpose. We've used the transpose method, which sort of like now it will make the columns our rows, and it will make the rows our columns. Okay, yeah. So now maybe we can answer these questions, and then there will be an exercise for you to do later on in the summer school. So one of the skills that data scientists should have, and well, data analysis is sort of like part of what the data science people do. And one of the skills that a data scientist has or must have is maybe what we call substantive expertise. And with substantive expertise, basically what we mean is that if at all you have this information, you have this data maybe lying on a website, maybe lying on some social media platform, can you sort of like create meaning out of it, okay? And also with substantive expertise is, can we be able to get the substance out of the data, the value out of the data? So how we do this from exploratory analysis is we have to be able to ask the right questions, okay? Because when we ask the right questions, that is how we shall be able to get the insights in the data, the patterns in the data, and so on and so forth, okay? So these are just a few questions that we have in the data. And yeah, so they sort of like begin from very simple and then maybe a bit hard like that. Okay, but we are going to do them together. So the first question is, what are the number of rows and columns in the data? Okay, so for us to do that, we call our data frame, and then we do a dot shape on it. So the dot shape is a method that returns two values. So it returns the rows in the data, and then it also returns the columns in the data. Okay, so take it like a matrix that sort of like returns row by column. So you can see that we have up to 26,982 records or entries, and we have 11 columns, okay? Then the second, the number of columns in the data, okay? Yes, the number of columns in the data. What are the columns? So the number of columns in the data, we've sort of like already returned it, but if we want to be that specific, then we can go ahead and mention the position, okay? So since we know, or since we've said that this is a matrix that is returning two values, one which is sort of like housing the rows and the other which is sort of like representing the columns, then we know that whatever is in position 0 is the number of rows, and whatever is in position 1 is the number of columns. So to return the number of columns, we just, on dot shape, we just mention the position to get something like that. So, but maybe we can also think of returning the columns themselves. And I think this is something that we've already done from up. So I can stay with this here. Yeah, so here below we return the columns, that is the names, the column names, and above we return the number of columns. Okay, question 3, number of countries reported on in the data. So now we are talking about the number of countries, but maybe someone might be wondering where the country is coming from. But if you've done dot columns, you've actually seen the column names, because in most cases, even if you're sort of like creating your own data, it would be good for you to create variables that sort of like make sense. Yes, that if someone sees something like countries and territories, maybe they get to know that actually this column is holding the different countries that we have in the data. Okay, so if you've done these dot columns and then you come across question like question number 3, the number of countries reported on in the data, then you can be able to extract out that, because you know the particular column that is holding that information. Okay, and that being these countries and territories. Okay, so if I do this, it's going to return this in form of a series. Okay, but now the question is, I'm supposed to return the number. How many are they? Okay, so now I should think about using a method called unique, because we know that since we are logging per day, we have more than one entry on a given country. But if I do unique, then it will return the unique. It will return each country once, okay? Something like that. So I go ahead and I add n to have a method called n unique, and this stands for the number of unique countries for this case. So you can see that there are 210 countries, okay, in our data. So when I was doing research, I found out from the Worldometer that we actually have 195 countries in the whole world. So now maybe these are sort of some of the questions that you can think about and see if at all you have any errors, okay? Because later on, let's say if you're going to use this data to maybe do some prediction, you very well know that having incorrect information will affect your model. But also, even before we go into prediction, if at all we are to sort of like present a report or tell a story out of the data, we know that if we have this incorrect information captured, then part of the story that we are telling is sort of like misinforming the audience. Okay, so those are sort of some of the things that you can think about. Yeah, that if there are 195 countries and here we sort of like have 210 countries, do we sort of like maybe have certain values represented as countries, yet actually they're not countries? Maybe do we have maybe do we have city names included there, things like that. Okay, yeah, so maybe it could require you to bring in another data set and you make your comparison, etc. Okay, but those are sort of like the insights that I'm talking about. So let's move to question number 4. So question number 4 says, specify the countries captured in the data. Okay, so we've already done that. We've already specified the countries captured in the data, and I can sort of like just copy this and bring it here. And so these are sort of like the countries that are captured in the data, okay? Then the other is number of continents in the data, okay? Number of continents in the data, because we know we have a column that is holding the continents. We can sort of like say, I think it was this. So there are 6 continents, okay, that are specified in the data, but still we know from our sources or we know that we have 7 continents, right? So we have Africa, we have Asia, we have Europe, we have Australia, we have America, that's South America, and North America, among others, okay? So now if we have like 6 continents, that means that maybe there is a particular part of the world that was not captured in the data, okay? So for example, even before we go ahead to think of the next question, so let us sort of like see what are actually those countries that we have in the data. Sorry, the continents. So we see we have Asia, we have Europe, we have Africa, we have America, we have Oceania, we have other. Now we all know that we don't have any continent called other, okay? And now this is where the cleaning comes in, the data cleaning. So the next question is actually as a result of that, and the question is, which country or countries is or are included in the continent named other in the data? Okay, so we'd want to see which country is that, yeah? And given the country, then we can point it to the right continent that exists, yeah? So we've seen there is a continent called other. So if we are to extract that particular country, and then we're sort of going to say COVID data. So we specify the condition. And the condition is where the continent is other. Something like that. Okay. Okay, so this is returning a data frame. So maybe we can actually only return the country since we are interested in getting the countries. Okay, yeah, so this is the list. Still, it's very long, and you can see there are those 3 dots. Yeah, so if we do a dot unique, we can see that it's actually only one country, and this country is called Cases on Non-International Conveyance, Japan. Okay, so so let's say this country is Japan. Okay, we know that Japan lies somewhere, I think South Asia. Yeah, so we know that maybe Japan lies in Asia. Okay, so what we can do is we can now sort of like think of using other functions that can help us to replace this value called other with Asia, okay? Since we know that Japan is in Asia, and then we can maybe also replace the value itself. Instead of having cases on an international conveyance, etc., we can sort of like replace it with Japan itself. Let's see question 7. Okay, so before we go to question 7, because question 7 now we go into, so we sort of like go into an analysis on Africa, since this is data science Africa. Okay, so I'm saying now we are going to think of using a method that is called replace. and it's basically going to help us to replace whatever we had earlier on. Okay, so I can say this is Kelly, and it was captured in the countries and territories. So we can sort of like equate, and we're going to say that our new column is going to have something like this. So it's going to be equal to this, and what we're going to do is that we're going to replace. So we're saying we're replacing this we're replacing it with, let's say we're replacing it with, so we're replacing it with Japan, maybe. Okay, just a minute. Yeah, something like that. So if we've done that replacement, and then maybe call this column, this code again, yeah. Then you can see that now it's Japan, okay? And now the next thing for us to do is to replace other, okay? So we're going to replace other with Asia, because we know it's holding information from Asia. Or it's holding information in a country from Asia. So I shall say for the data, and that's continent, that's real. So saying equals. Yeah, so we're replacing other. So whatever I would want to replace comes first in the method, and that whatever we're replacing it with comes next. So I'm sort of like going to make sure I write it in the same way because I already have a value called Asia, okay? And these are entries that I would want to be captured under Asia, right? So let me connect this out, something like that, okay? So if I do this, and then maybe I do unique again on my on my column that is holding the continents, then I can see that I've eliminated other, okay? Because it was not really making sense. And I've seen that it's holding information for a continent, for that continent called Asia. So that was that. Let's move on to question 7 very fast. How many African countries are in the data? Okay. That's question 7. So I can do this, then we specify that we want only Africa. So maybe one of the problems that is with this data is that it was not geocoded. And that means that actually, if at all there is an entry that does not, let's say, belong to Africa, but it was tagged under Africa, it's sort of like hard to find out, unless when you specify all the countries that are in Africa, something like that. But if it's geocoded, when you plot, at least you can sort of like see those outliers in the data that come in as mistakes. So for now, we cannot see that, okay? Yeah. So the question is how many countries are in Africa? So I have countries and territories as a column. So I say return this, but maybe return the number of countries using the N unique, and I can see there are 55. There are 55 countries. So you can still ask the same question that we asked ourselves, but we can see that if at all this data source is fetching data on 210 countries, but only 55 are Africa, but only 55 Africa, then we can see that actually the largest representation is not from Africa, or maybe until we do sort of like a group by on a continent in terms of counts. Okay, so those are the number of countries. Then question 8: which African country had the highest total cases in the month of June? Now we are sort of like going deeper. Okay, so the question is, which African country had the highest total cases in the month of June? So that means that first of all, we are interested in African countries, but second of all, we are interested in the month of June. Okay, and we are sort of like supposed to find, so it's sort of like supposed to find the highest value that lies there. Okay. So we go ahead and specify those those given constraints that we have, okay? But maybe to reduce, to sort of like reduce. So since we already have this here, we'll just copy it. And then maybe I can store it in a variable called Africa, COVID data. Yeah, something like that. So that at least I have a smaller set. At least I have a smaller set to work with. Okay, so I can do that specification. Then after that, I can go ahead and now specify the next constraint. So the next constraint was I'm interested in the month of June. Africa COVID data, the month. So the month is June, and for now our months have been captured as numeric entries. And this sort of like returns only cases that were registered in June in Africa, okay? Yeah, that one only returns cases that were registered in June in Africa, right? So we can sort of like now, because remember we're interested in country, so we can sort of like go ahead and see how to sort of like break it down more further. So for example, if we say that this is June data, yeah, I can say that I'm interested in June data. Yeah. So if I say cases, yeah. So the highest cases that were registered at once was 7,210. But I'm interested in the country that registered those this number of cases. Sort of like, sorry. So where are cases? So where we had cases equaling to that, okay. Yep, something like that. Okay, and so this returns that entry, but maybe I can specify here that return something like that. Okay. Yep. Okay. Just correct this. Okay, yeah, so returning something like this. So you can see the country with the highest cases, that is South Africa. And that was on 28th June, where they had up to 7,210 cases registered in a single day. Okay, something like that. So I can move to the next question. That's question 9. When did Uganda register the first COVID case? Okay, for example. So to do that, sort of like what we're going to do is that we are going to fetch out Uganda data and then have a smaller data set for Uganda. And then I think we can actually do that on COVID data. So from COVID data, sorry, we can get that where countries and territories equals Uganda. I think it's written like that. Yeah. So these are the Uganda cases that we have. So you can maybe name it Uganda COVID data. Yeah. And so maybe we can sort of like re-index. Say reset index. Maybe since we don't want to store that value, drop it. So you can drop that value. Then you can say Uganda COVID data equals to that, I guess. Yep. So when you call this again here, yeah, we have, so we have our data organized like this. But I think from observation, you noticed that we had our data organized in alphabetical order, okay? That's why we had Afghanistan first and so on and so forth. Yeah. But now when we look at the date, sort of like begins from the time we had the first case up to the time when we collected the data. And as I've said, we collected this data on, we collected it on 1st July. So that's why we can see that. Okay. Yep. So we can now think of maybe returning the data by sort of like indexing. Let's say Uganda COVID data. Silo. Let's say -1 because that sort of like refers to the very last entry. And since we're only interested in returning the dates, then you can mention this, something like that. So according to this source, our first case was on 22nd March, 2020. Okay. Yeah. But maybe we know from media it was 21st, I'm not sure, something like that. Then the last question for our trial is how many countries have 0 death up to date? So in other words, how many countries do we see where we've not registered any death up to date? Okay. And but remember, we are sort of like saying that this is daily data. That means that maybe on one day it can be 0, then on the other day it can be 1, then on the other day it can be 2, something like that. Okay. Yeah. So that means that we are first of all going to sum up the death, but we are going to do that after grouping by countries so that we know the countries where we don't have any death. So we're going to go back to our first variable name since the question is now referring to the entire data set. Yes, okay. So I said we're going to group by it's countries, territories. And then you can sort of like say that. And we do a summation because wherever it's 0, still it will just keep on adding 0 plus 0 plus 0. Okay. So something like this. So you can see Afghanistan out of summation, it has had 746, but countries like Angola has had 0. And this Bhutan 0, Bonaya 0, like that. But now we're interested in sort of like knowing how many countries are they, okay, where we've not had any death at all. So maybe we can subject this to a variable of a death equals. So I can do to end up with something like this. Okay, subject it to a value for COVID death equals here. So that I might have COVID death as that. Yeah, so since we're interested in the ones where it's 0, then you can specify here where we have death as 0. Okay. And these are the countries. Okay. So we can do, we can apply the length on this to what is this? Okay, let me just do this, take it away from here. Run this. Okay, then I can sort of like and I can sort of like run that.
Claire?
Yes. Okay.
All right. I got to remind you that your time has clocked, but you have a few questions that maybe
Okay.
you can answer to, and then yeah, and then you can end there. But
Okay.
yeah, but Claire is going to be available. I don't know. Yeah, maybe during the break, people can you know, chat a bit with her. Yeah, so there is one question here. It is in line 119 or 122. Why did you use a reset index?
100. On which question exactly?
I think here he has quoted the cell numbers.
Hey,
So
okay.
go to 100 and
Can he quote again? Because I don't have 119 anymore.
there is a reset index here.
This one?
Where you have, yeah. Yeah.
So it's asking why did I reset?
Yes.
Okay. So okay, if you look at and I know that effect has already happened. So if you look at what I have here, okay, as information that is returned, this is sort of like not in a data frame, okay? It's like this. It's sort of like capturing the countries and territories, and then I know that this is the summation per death, okay? But remember, I would want to do further analysis, and that further analysis is to sort of like specify that where the death is 0, yes? So the reason why I did a reset index here, so that I can sort of like come up with something like this. And this is the data frame that I'm talking about. So I can now go ahead and specify, as you can see here. Yeah, yes, so that was the reason for reset index.
Okay. Then there is another question from Timothy. And the question is, my question is on automation of data input. The ministry releases cases every day, and online trackers pick up this data. How do online trackers pick up cases and make updates to their sites in real time?
Okay, so I believe if you sort of like want to keep on fetching data in real time, there is code to that, or there is script to that. So it's basically coding. You code so that you link to the website, and then maybe you can fetch from the website. It can be in real time, it can be after every 5 minutes, and so on and so forth. Yeah. So what we did, we just downloaded it and now brought it in the notebook. Otherwise, someone can link to the URL or to the website directly.
Okay. Okay, I think Timothy has been answered, but other systems do have APIs, application.
Yeah, then there is API. Program
interfaces that, can help to, fetch the data as it changes, the APIs are able to pick the data. Okay, thanks, Claire, for the presentation. I think, it has been good, very clear, and I think the participants have got a lot of insights on how to use pandas, and the lists of questions are still there. The participants are encouraged to practice those. So thanks a lot, Claire.
You're welcome. Okay, sorry. So I already shared the notebook with the program coordinator. I think you'll be uploading it, yes.
Yeah, so the notebook is going to be available online. You can check. You can check the DSA, the Africa.org website, and then you'll be able to see it there. So the next presenter is Mike Smith from Sheffield University, and is going to be taking us through. Mike, are you able to share your screen? Mike, can you hear me? Mike. Yeah, so maybe Mike is still yeah, so as maybe Mike is connecting, I would like to share my screen, just update members. Yeah, just maybe to update members that the schedule for Data Science Africa, we have it today, tomorrow, and then we shall have it on 28th and on 29th, that is for the summer school, and then we shall have a workshop on 30th and 1st. Then the other update is that we have a data science research award, which was announced some time back, and the deadline is 15th August, so members are encouraged to visit the website to register, to send in their concepts. Then people are encouraged to follow our Twitter page at DSA_ORG, and the hashtag we're using today is #DatSciAfrica.
Martin, I think Mike is ready.
Mike is ready.
He just got a small, but he should be ready. Let's
Hello,
see if
hi. Yep. Can you hear me?
Yes, we can.
Hey, good stuff. Hey, it's good to be here. Hi, everyone.
Hi. So can you try to share your screen?
Sure, yeah, I'll give it a go anyway. We'll see how that goes. Hopefully that's working. Right, so I can't see the chat, right, because I'm looking at my screen now. So if there's any questions, can one of you just like say out loud so I can hear you, because otherwise I won't be able to. I can't see any questions or the chat or anything. So yeah, can you see that? Can anyone see my screen?
Yes, Mike, we can see it.
Cool, great, cool. Well, it's good to be here. It's a bit earlier in the morning than I'll be like used to. So yeah, time zones. Anyway, yeah, that looked like a really useful introduction to the notebook, and as well as the like COVID and how to analyze like different data sets. That's a great talk. I should have come earlier so I could have learnt a little bit more. But hopefully that'll be useful for messing with the notebook I've got for this project. So what I'm going to do today is talk about classification. But to be honest, I realized when I was making, actually I quickly edited the slides this morning because I sort of realized I'd gone so far off topic, it wasn't really about the classification at all. So it's about lots of different machine learning related topics. And then after that, there's a notebook on Google Colab that I'll put the link to that everyone can have a go at for half an hour maybe. And then I'll link to the answers and we can look quickly through some of the answers to the questions. And if anyone has any questions during the presentation, just say in the chat. And the thing is, I wouldn't even know if I'm disconnected, so I literally might just be talking to myself. So every few minutes I might have to go back and check to see if I'm still even in the call. Right, so machine learning. So I thought it'd be useful just to like, there's so many different terms floating around. I thought just a quick detour to think about what on earth that means, right? So for me anyway, all of these different things, artificial intelligence and data science and applied stats and things, all revolve around learning from data. Okay, so it's pretty broad, but it's instead of using like a model that maybe models a physical process where we don't need to worry about measuring it, like learning from data where we can use our like predictions from physics, say. Here we learn the structure of our world and its behavior from data that we've observed. Okay, so that's sort of like what sets machine learning apart from maybe other areas. Okay, that's sort of like, I don't know, from a really high vantage point, that's sort of my understanding of the term. I just think it's quite useful to sort of think about what we're doing. So today we're going to be talking about, I'm going to detour completely. Can people see my cursor, by the way, Joyce or Martin? If I point, does that show up?
Yes, I can see it.
Okay. I was just checking, great. So complete detour. I'll talk about a few other projects that I've been working on, and sort of, especially for the bee tracking and the adversarial examples, these connect strongly to classification. So that's why I'm sort of like motivated by them. And then I sort of like look at classification and we'll look at a real example. And then I sort of have a detour to linear regression just to go through some maths that's applicable to the classification, but it's probably more easily introduced with regression. Then there's a bunch of other topics on classification. Then I quickly mention convolutional neural networks, and we'll look at other applications of machine learning. So really quick detour. This is like a project. I don't have the tracker on my desk at the moment. This is a complete detour, but it's kind of a fun example of why, like, where I'm using classification in a real project. Okay, so this sounds crazy, but I've got a project that's been running for a few years now in my spare time where I'm trying to track bumblebees. Okay, so you don't get bumblebees in Africa, I think, because it's too hot typically. They prefer temperate to cold environments where their fluffy, furry coats sort of give them an evolutionary advantage, as it were. So that's why that you find them in cooler climates. Okay, so but you'll have something similar, I guess. So these bumblebees like reach about from plant to plant, okay, and collecting pollen and nectar and so on. Okay, and there's hundreds of species of bumblebee, there's thousands of species of bee. But the cool thing is, and there's obviously millions of types of insects, and researchers know really relatively little about pretty well anything. Like, it's amazing how, like, solitary bumblebees, there's hundreds of species of them in the UK. We have no idea about, like, what they prefer to eat, how far they go, like, you know, how, like, where they like to put their nests. We know like frighteningly small amounts about these creatures. And one problem is we can't track them, right? Because, like, they're so small, you can't put a GPS tracker on a bumblebee for obvious reasons. The nearest that they've got is a radar. So I've got this other option where you stick a little retroreflective sticker on the bee, okay, like I did to this one. and then you let me find a picture. You get like a gadget like this one that I've just put together, and you take pictures with and without the flash. And I don't know whether you can see it, probably won't really make it over the internet, but this is a picture without the flash, and this is a picture with the flash. Okay, and the only difference is basically retroreflective objects. What you can see is a little dot just there that disappears and reappears between the two photos, and that's the retroreflective dot on the B. Right, and the cool thing is, like, as you can see, like that shows up quite brightly. And what you do is you take these two photos and subtract them, and you're left with basically nothing except the reflector. Okay, that's the idea. Okay. Now in practice, I found this didn't work quite as well as it did in this sort of experiment I did once. In reality, there's loads of other stuff that causes problems, like pale coloured butterflies mess it up, or bits of litter, you know, reflections off, like leaves fluttering in the wind, often sort of glimmer quite brightly. There's like raindrops, bits of pollen floating past. There's loads and loads of false positives that mess up the system. So I've had both an undergraduate and a master's student working on this project, and we've been developing a really simple classifier, to be honest, to try to classify whether or not this bright dot is really a B, or like really our reflector, or whether it's some other bit of like false positive causing a problem, like butterflies or whatever. So what we did is we had to collect some data. So we went out with a reflector on a stick. I don't think I've got a picture of us wandering around with a stick, have I? No, okay. We wandered around with a reflector on a stick, pretending to be the bumblebee, right? And then took loads of pictures, and then we were able to label afterwards where our reflector was in the pictures, and then we could use that as training data for our classifier, because all of the points that weren't that spot we knew are false positives. Okay. So we used, and the classifier we ended up using is I think the one I'm using is just a support vector machine, really standard, bog standard classifier, but it's like massively improved the quality of the system. So yeah, that's the just being able to grab off the shelf a classifier and apply it to problems is quite useful. Yeah. So here's some pictures of us messing around. So we tried putting it on the top of a mast as well, just because then it could look down on the landscape. Here we're trying with tethered balloons. So this is like the life of a machine learning scientist, I guess, having to do lots of random experiments. It's quite fun. Anyway, yeah, sure, go ahead. Yeah. Do you have a question or something? Or
someone is putting up their hand. Let's just take it, and I don't know what. Yeah, and hear the question. Pius, can you go ahead? Pius.
See, is someone's saying my what's the sound not clear? I don't have a separate microphone. I was hoping it'd be clear enough. Thanks for the heads up. I'll just try to talk clearer and slower and closer to the computer. Where's the question?
Yeah, yeah. He did not talk, but I think you can go on with your presentation.
Okay, I'll try to be clearer and put my face nearer the computer. Right. Right. So this is like has classification aspects. So this big project with Engineer in Kampala, which I'm sure Engineer will get to talk. Hopefully, get to talk about a bit more. So really briefly, one obvious classification problem is, can you classify for sensors failing or not? That would be a really useful like classification task. But I'm not going to dwell on that project. One other project I've worked on in the past is looking at adversarial examples and adversarial attack. Okay. So this sounds completely mental, but I don't know. Actually, interesting. Who's already heard of adversarial attacks and adversarial examples? Does anyone? Do you want to say yes or no? So it can be adversarial examples. So yeah, who's heard of these? Just out of interest. Oops, that's like a private chat instead of to everybody. Cool. Yeah, okay, cool. Quite a lot of people have heard of it. Okay, yeah, so just briefly to those who haven't, you might train a deep convolutional neural network on natural images. Okay, so these are like pictures of animals and wildlife and all sorts of things. And then you could give it a picture of something it's never seen before, like this little dog, and ask it to classify it. Okay, and it says it's a dog. Right, I don't even know what breed it is, but anyway, looks a bit stupid. But anyway, right, okay, so it's found a dog, and that's fine. Okay. Now the weird thing is you can add a tiny perturbation. This is the sort of scaled up version of the perturbation to generate this image. Okay, so this is a different image from this image. Right, honestly, like there are differences. Like if you have a look between its eyes, there's some dark lines there. See that aren't in this image, you know, and then there's what else? I can't even see any differences. But anyway, there's a marginal change. This image gets misclassified as an ostrich, I think, in the example in the paper. Okay, and this is like it's a bit ridiculous, and does it really matter because it's a dog? But it's really easy. Like it's relatively easy to do, and you can do it to pretty well any image. And there's things like, I don't know if I've included it in here, but there's universal perturbations. This perturbation here was generated specifically for that network, for that image, okay? But there are universal perturbations that can apply to any network for any image, as it were, and cause misclassifications. So that's quite a severe problem, probably. Like, how can such a small change cause the classifier to get it so wrong? Okay. And like, yeah, you can say, oh, well, it doesn't matter, it's a dog, okay. But there's this example here, for instance, where I should have put the references at the end, sorry, I've forgotten which paper it's from, where the researchers, I think it's Papanu, anyway, the researchers like try to segment the image into like road, background, pedestrians, other vehicles, or whatever. And this is like the segmentation, so they can sort of see the humans have been segmented as these people. This is the same, like nearly the same image, but with the perturbation. Can you see it looks a bit different? Okay, and this is what the classifier, how it does the segmentation here. Now, I guess like if this is controlling a self-driving car and it's deciding whether to like drive forwards, ideally you want it to stop if there's people in front of the car. Assuming you like the people, then in this case, it's clearly going to keep going. So this abstract example is actually like an example of like a maybe more serious problem. Okay. There's another example here where this researchers have like stuck labels on a stop sign. Okay, and so on this side they've stuck the labels on the stop sign. This side they haven't, and the classifier misclassifies the stop sign as a speed limit sign. Would if the so this is the label that is classifying the sign as. So the idea is like even just a few stickers on a street sign could cause the classifier to misclassify. So yeah, it's sort of like an important problem that we haven't quite got to the bottom of, how to like really protect our classifiers from this sort of attack. Okay. Yeah. So back to sort of standard machine learning, just to sort of go back to basics. So sorry, we're changing topics now. This is what I meant. I sort of stuck in lots of extra random things. So machine learning sort of is divided into two main broad areas, like supervised and unsupervised. So supervised is where we've got like some sort of like label associated with each training point. So we know, like with the bumblebee one, for example, I've labeled which points are really the bee and which ones aren't. For a different project on looking at patient data for motor neuron disease that I worked on a little while ago, that was like looking at sort of an exploratory analysis and was effectively unsupervised because we didn't know the subtypes of motor neuron disease that the patients had. We're sort of like trying to identify and learn what they might be. Right, so of supervised, there's sort of two areas. There's like classification and regression. So really obvious, stating the obvious here, like regression is like basically where you're trying to predict a value associated with a training point. Okay, so you might be trying to predict the value of the dialysis patient's blood pressure. Classification is just where you're trying to like put a training point or test point into a class. Right? So it's stating the obvious, but it's just important to keep in mind these are the sort of two main areas. So you might want to say whether a patient has high, very high, or low blood pressure. Okay. Right, so we've got a real problem, just to give you sort of like ground this in reality. So when I was in Kampala many years ago, my now wife was working in the in the main hospital in Malago at the nutrition unit, and there they had like children arriving every day who needed, or some of them needed sort of extra feeding. So some needs to be treated as inpatients, and some could just be outpatients. And they had a series of processes to decide which children needed to be an inpatient. And so which children need extra feeding is kind of the question. So I've kind of oversimplified the true clinical way they do this assessment for the purposes of the presentation. There's a lot more to it than this, like knowing their history, their siblings, their other comorbidities, and other factors. But just for simplicity for this presentation, we sort of have simplified that. So deciding which children need to be inpatients is we need to do classification, right? So they need to be an inpatient or an outpatient. Right? It's a classification problem. And we need, if we're going to do it in a machine learning way or data science way, we need some training data, okay? And this consists of previous children, okay, to decide on the treatment. Okay? But what features of the previous children are important, okay? So the color of their hat isn't an important feature probably for deciding on whether they should be an inpatient, okay? So it's important to pick our features that we think are sort of relevant to the problem. Okay? So the two most common features in the field of acute malnutrition are arm circumference, or it's called MUAC, middle upper arm circumference. That's there. Or weight score. Okay, this is like a where you divide your weight. I can't remember if it's by your height and stuff, and it sort of gives you a standardized score to say whether or not someone's got a low weight for their size, effectively. And it's there's sort of advantages and disadvantages of each of these. So the arm circumference is kind of harder to measure, but maybe it's more useful. The weight score is easy to measure, but maybe it's less powerful. So there's maybe using both is also maybe the way to go. So actually in the unit, they did both to try to make sure they pick the right children. So this is made up data, to be clear. This is synthetic data, just to illustrate the problem. So along the bottom, we've got their arm circumference. That's their middle upper arm circumference in millimeters. And up the side, we've got this normalized weight score for each child. Okay. And the red crosses are the children that needed to be inpatients. Okay. And the green crosses are the ones that can be outpatients. Okay. And we've got a new child at this question mark that we don't know. Okay. We need to decide, using these previous children, whether or not this child needs to be an inpatient or an outpatient. Okay. So does anyone have any suggestions about whether that child should be an inpatient or an outpatient, a red cross or a green cross? And I'll be interested, if you could give your reasons as well, that'd be great if you want to. Feel free to make your suggestions. I wonder if I just turn off full screen, then I can see the chat at the same time. So, oops. So do people have a suggestion about what the question mark should be? Even if it's just a random guess, what would you do if you were there? Cool. Okay, we've got an answer. Good stuff. So treatment not required. Cool. Vanon's got a good point as well. It depends on the model. Cool. Okay, so it looks like 3 people so far say it's not required, and oh, good. Seku's given an actual reason as well because it's close enough to the others of that type. Cool. Right. Okay. It looks like there's a majority now going for not required. Does anyone else have any other opinions, just out of interest? Can anyone give the other argument? Cool. Colin's given a bit of uncertainty there, probably. I like that. So, Vernon, it's true. Yeah, exactly. It depends what kind of decision boundary we're going to use. But that's kind of what we're deciding, right? So we need to decide on a good decision boundary. Cool. Someone, I'm happy to saying on the borderline. So this are quite good points because it's we aren't. Some people are expressing uncertainty about whether or not it's required or not. and I think there was an interesting point, this one here, so it's close enough to the others of that type. So this is a really good point. So if I start here, right, so if you have a look at this one, in general, the ones nearby this one roughly are of green, right? But actually the nearest one is this red cross, okay? So if you just looked at the nearest one, like rather than the one that's sort of the general area, then the nearest one's actually a red cross, right? So maybe treatment is required. So, but on the other hand, what you're saying is like it's close to others, sort of like more than just one. So maybe the way to deal with that is like look at the nearest like 2 or 3 or 4 neighbours and see what they are. And that's basically you've sort of invented a classifier called k nearest neighbours, okay, which is where you look at the nearest, like say the k equals 5, the 5 nearest neighbours, so this one, this one, this one, this one, and maybe this one, I don't know. And you sort of like look what the majority is. So in that case, 4 of those 5 are not required. So that's what we'll assign the class to. So that is a common classifier to use, and it's quite powerful in many cases. Right, so there's this other thing about the uncertainty. So where's the other uncertain thing? Where someone wasn't sure. Depends. On the borderline, yeah. So this point about uncertainty is really important, especially when it comes to something with a high cost if you make the wrong choice. So just a quick detour, you might want to err on the side of caution and be like, well, even though it's kind of near the not required thing, we maybe should put them into the required thing just because it's sort of on the borderline, right? As someone said, right? So, you know, if it'd been over here, then maybe we could be like fairly confident the treatment's not required. But as it's over here, maybe like there's a chance it is required. And to deal with that, we can do it formally. Like you can just do hand waving and just say, yeah, let's don't take the risk. But there's a formal way of dealing with this, which is like with a cost matrix or risk matrix, where you have effectively like the cost of inaction, you know, the cost of the 2 actions given the 2 possible conditions, and then you can you assign a cost to each of those. So the cost of not treating a child that does require it versus the cost of treating a child who doesn't require it, and the cost of treating a child who did require it and not treating a child who didn't, right? So you have the 4 possible combinations, and you can effectively, if you can assign a probability to that child needing treatment, then you can sort of multiply that with the cost matrix to give you like a sort of an outcome weighted by the cost of the different actions. So I haven't got a slide on that. I just thought I'd add it in just to mention it. But it's a useful, and it's kind of just a ranting detour. I shouldn't really rant and detour when it's like recorded in front of 100 people. But I do okay, in the UK, I wasn't very clear about why, like this is a COVID rant now, why the government made the decision to delay lockdown, right? And I do wonder whether or not, did anyone actually do that sort of analysis? So that would be an example where you might want to do that analysis, where the cost of locking down early might be economic. Supposing COVID wasn't that bad, and lockdown would have been overkill, and actually everyone would have been fine, right? And maybe in February that maybe wasn't so sure, maybe, I don't know. But then you could have the other extreme where maybe lockdown, like the disease is really bad and everyone needs to lock down and it's really dangerous. If you don't know, then you just have, you'd have to have probabilities for the different conditions. And the cost matrix lets you weigh up the pros and cons of these, you know, and lets you make a decision based on the values you assign to things and the uncertainty. So at some point you do assign some value to the economy, I guess, and people being able to afford food. But at the same time, there's some value to people not catching COVID. You need to unfortunately, some poor person has to actually make that decision about what that trade-off is. And the cost matrix is the way of doing that. So I don't know whether that was ever applied and whether more sophisticated methods exist, I imagine. I'm just curious, and I haven't found out whether that sort of thing was actually done during the COVID epidemic. But in this case, you've got the same thing again, whether or not there's an economic cost of feeding every single child at your hospital. You know, there's only so much capacity, so you need to make a decision based on both the cost of feeding them versus the cost of not feeding them. Right? So yeah, that's like where the trade-off comes. So hopefully that sort of like detour sort of explains why uncertainty is really important. Because if you haven't got uncertainty, you can't do that sort of calculation. Right, so we've got this puzzle of like the nearest neighbours is one possible solution. Another one that people mentioned, there was decision boundary. Cool. So this is like a different way sort of thinking about this. So rather than just sort of thinking about the nearest neighbours, we can maybe make a boundary on the graph and say all the ones on this side are like not required and all the ones on this side are. And that's like a valid way of doing it. And this is quite common, and it would be like logistic regression. Right? It would be an example of where this would be used. Now, we could have a more complicated decision boundary that sort of wriggles around, sort of, you know, goes around every single point, and that's valid as well. But you end up with, and that's usually what's necessary. But often you can end up with overfitting if you end up with a really complicated decision boundary shape. Okay. So we'll come back to that in a minute, but I just want to quickly detour and have a look at how we assess our classifier. Okay, so I've got a bit of text here, sorry. So typically we want to split our classifier, our data into training and test data. So I think you guys have probably already experienced this. This lets us like look at how well the classifier does, right? Because it trains on one set of data and is tested on another. And you can just do that once, but that could be quite inefficient if, say, you use up half your data for training and half for test. The problem then is your classifiers only had access to half your data. So, you know, it could have maybe done better if it had access to more. But if you gave it all but one and you test it on only 1 point, then you don't really get to find out how good the classifier is, because it's only got a, like, correct or incorrect for one data point. So what we do instead is we do something called cross-validation. And that's where we hold out one data point as our test data, train on the rest, and then test the one we left out. And then we put it all back in again, and then we pick out a different point, train on the remaining data, test on that one we left out, and so on. Right. So the idea is eventually we've tested on every single point, and we've trained on as much data as we can each time. Cool. Does that make sense? And have people, I assume, already heard of cross-validation? I just thought I'd sort of remind people. Yeah, any questions on cross-validation? So in our case with the children, if there's like 5 children, we might take out 1, 2, 3, 4 to be training data, and then child 5 might be test. And then maybe we leave out child 4 to be test, and we train on 1, 2, 3, and 5, right? And so on, until eventually we've tested on every single child. So, and so on, etc. Yeah, it's fairly straightforward, but it's just it's a quite useful technique. Right. So there are some caveats to that, though. Okay. So, sorry, this diagram isn't very good. I should have made it bigger. When splitting your data into the training and test, it's important to avoid accidental correlations which confound the evaluation of your classifier. So what that means is, imagine each of those children. So this is like supposed to be that I've got a different data set, made up data set here, but those children, imagine if they all had siblings. The chances are those siblings are going to be, well, they're from the same family, they're probably eating the same food, they're probably genetically more similar, so they're probably going to be quite, they might be quite similar in your NUAC and Z scores, right? So, and if one child from a family needed help, it's very common for another one to need help as well. So that's kind of a confound, because if you train your classifier and you do leave one out, cross-validation on that data, your classifier is going to like do really well, because like in this case, I should have made it bigger, I'm sorry people. In this case, this child here, we're trying to guess, right? But because it's right next to its sibling, the classifier can just be used k nearest neighbours and pretty well always get 100% in this case, right? Because every child you leave out has a sibling next to it who is just like them, right? So, I mean, that's obviously synthetic data, sorry, but like you get the idea that like because you've got a sibling in the data that can help you, you're kind of always going to do really, really well. In reality, usually you don't have a sibling that's already been through the hospital that can help, right? Usually a new child that you've never, that, you know, in a year's time, there's not going to be sibling data in your training set. It's going to be a new bunch of children. And so you won't have these siblings to help your classifier. So your classifier won't do as well. So if we if we just leave one out each time when we do our cross-validation, we're going to be like overly confident about our classifier's ability, right? So in this case, we'll get to like 100%, and it will look like the classifier does really well. When in reality, if you think about it, if I give you a new sibling group, you know, if both of these are question marks, it wouldn't do at all well. It would be really hard for it to predict whether it needs help or not, right? So does that make sense? Is there any questions at this point? So I should have made this picture bigger, sorry. But the idea is you need to, like, when you do cross-validation and you take out your training data, your test points from and split your test and training, you want to, when you do your training test split, you need to make sure there's no correlations between, like unwanted correlations between your training and test data. Yeah. Does that make any sense? Does anyone have any questions? I feel that's quite like an important point. It's not that hard once to get your head around, but I might not be explaining it very well. Does anyone have any thoughts or maybe even examples where you've seen this sort of thing in your own data analysis?
Mike, we have a question.
Oh, right. I forgot about questions. Okay. I forgot they don't always appear in yeah, go ahead.
Yeah, he's asking, is it a good practice to use cross-validation on big amount of data?
Yeah, so when you have loads and loads of data, then you're going to, like, say you've got 1 million training points. You won't be able to leave one out because it would take too long. So we usually use then k-fold cross-validation, it's called, which is where we split our data into maybe like 20 chunks and leave each one out. So, but yeah, you can still, you just still use cross-validation on that as well. Yeah, definitely. One other thing that's worth doing, I wasn't going to mention this, but it's actually more important, is it's probably best, if you want to really have a gold standard on validating your classifier, is you should really have another data set that you expect your classifier to be used on in the future that hasn't been involved in the training or anything at all, right? So it's sort of held out until you're finished, right? And at the very end of your project, when you've made this clever thing, and you're really pleased and you've written it to a Python module and everything, then you apply it to this other data set that you've not looked at before, and you look at the quality of the classification on that. And that's important because it might be from a slightly different area or something, like, and this will check to see if your classifier can generalize to like really sort of like areas it's not exactly seen before. So actually for the Bumblebee project, one of my students got really upset because it just wasn't working very well on her. So I made her do this. We took pictures in one area, like where there's quite a lot of trees, and then she tested it out with like a final data set which was from a field where there weren't very many trees at all. And the classifier didn't do very well, right? And it's interesting. It's like basically the training data we had wasn't sufficient to generalize to this other environment. Okay, so having like some sort of separate data is like a good idea. Oh, there's another question. Since we use the validation accuracy, yeah, okay, I'll get to that, Vernon. That's a good question. Okay, so let me get to Vernon's question first. Okay, so, oh wow, I did have a bigger picture. I thought I did. Okay, so this is just this point, bigger, right? So yes, this is Vernon's point. So there might be hyperparameters. Exactly, there we go, cool. There we go. That we can adjust in the model, okay? So in the really simple k nearest neighbor thing, the number of neighbors, right? So k could equal 1 or it could be equal 11, right? And we need to sort of adjust it to like make it as good as possible, I guess. The thing is, if we just keep messing with it with the training and the test data we've just been discussing, we'll end up cheating effectively, is what do you say? So I think Vernon says it better than I do. It'll make it really and result in overfitting. I don't know whether it's necessarily overfitting exactly, but it will bias the more accurate. Yeah, that's interesting. Oh, I see. This is a slightly different problem. This is one about like overfitting and rather than about generalization. It's an interesting point. I don't know whether it necessarily will always. It depends on what the actual model is, I guess. So. I think the problem is more you end up with your. Okay, there's sort of two different problems here. So overfitting things is one of them, and we can get back to that. In this area about validation, the problem with doing what Vernon's talking about here and his concern is that actually it means that you overestimate your confidence again, right? So if you imagine you've got like a million hyperparameters that you can tweak, like all sorts of things, like the number of nearest neighbors, or like loads of different parameters can exist for most classifiers. If you tweak those to make it perfect for your training and test data, then you're going to overestimate how good your classifier is really, because you've kind of perfected it for your particular data, right? So to that end, we need to hold out even more data. So you end up with this little loop here of training and validating, which is what we were just discussing, where you're adjusting the number of nearest neighbors, or like number of or like the like, I don't know, what's it called, regularization in your support vector machine, or the number of layers in your deep neural network, or whatever it is you're fiddling with. Okay, what you need to do then is hold out more data that you wanted, like when you finish faffing about with it here, you want to then test it on this data. And that's kind of what I was talking about a little bit about the generalizing as well. So maybe you want your test data to be from another domain a little bit, that's sort of slightly different maybe. So for there was a dialysis project I was involved in, and we held out a database from a different clinic, set of clinics, because we want to be able to show that our method can like be used in other areas, like should be on the same data, but basically, we didn't want to like overfit on the data we already had. So yeah. So Vernon's point is basically right. Yeah, so this is overfitting, I guess. It's not quite the same, but yeah, it's in the same area. Yeah, we can discuss overfitting and stuff more later. Cool. I think actually that gets discussed in future talks quite a lot, so maybe I shouldn't talk about it too much now. Okay, please comment on recent approaches to perform a three-way split train test in deep learning. I don't know what recent approaches there are, to be honest, especially in deep learning isn't my strong area. Like, it's not particularly my area. So maybe, Osbert, you might be able to comment better than I do, to be honest. But it's just this point. You kind of want to split your, you need to keep your data separate, basically, to like your test data separate, so you can sort of really see whether or not your classifier is properly generalized. The more you break data into chunks. Do you mean into chunks? What do you mean by? I don't know. Do you want to explain a little bit more, Jonathan? Like, how do you mean? Do you mean like if you do like more k folds, like if k was bigger, or do you mean like splitting it into like more, having to have separate test data or something? I don't know quite what your question means. Sorry. What's the difference between validation and test data? Yeah, so the validation data, this is where you're faffing about with like the number of nearest neighbors, right? So what if you go back to the picture? We could try it with k equals 1, right, and do and sort of do the classification, and it'll get like, it'll do really well. Unfortunately, I've made this data set too simple, and it'll get like 95%, I guess. And then we could try k equals 5, and it might do even better, because then these two will be, let me think about this. Will it do better? Yeah, because like this one's going to be maybe misclassified and things. So, and then you could try nearest number that equals like 15, and it might do worse again, because you'll end up with like maybe the nearest 15 neighbors to this one are green or something. So there'll be like an optimum number of nearest neighbors, right? But that's sort of for this data, and by adjusting my numbers of nearest neighbors using this data, I'm now like, I can't then sort of assess how good my classifier is using the same data, right? If I did that, I've kind of cheated, So what you want to do is maybe take out like 20% of these points, hold them out as your test data, and then like perfect your nearest neighbor like parameter on the remaining data, and then at the very end, see how well you do on your left held out data. Does that make sense, Michael? Hopefully that cleared up. Yeah, and Jonathan, if you want to like post another message, I don't really understand quite what you mean. I don't see why it necessarily cause overfitting. I don't quite understand the question though. Yeah, maybe get back to me if you still want to, if I can help with that. Right, so how do you assess our classifier? Cool. Right. So that's some sort of like, it's rather like, I don't know, it's just the basics. Like, it's not that exciting, but it's important. Okay. So if you get validation wrong, then it means you'll end up like misassessing how good your classifier is, which can be really bad, right? Clearly, you don't want to like over promise sort of like an approach. And it's quite a common problem, right? You know, like it's not that simple. Like these correlations, for instance, are really obvious here, but in some data sets, it's a lot less easy to see where these patterns are coming from and things. So you have to be really careful sometimes that you're doing your cross-validation correctly, that you aren't accidentally cheating. I should probably detour and explain. So in my PhD, I was faffing about with functional MRI, so fMRI, where we were looking at like the activity in the brain under different conditions. And there's kind of quite a lot of lag in the brain in terms of the fMRI signal. So between your brain actually thinking about something, as it were, and the signal appearing as a change in the amount of oxygen in your blood, there's like a 3 or 4 second lag. And so you can imagine, and there's quite a lot of smooth. You need to be really careful. You can't just leave out one, like, so the data's sort of multiple like volumes, as it were, over time, maybe one every 3 seconds. So what you want to do is you kind of can't just leave out one volume, because the ones next to it are going to really tell you a lot about the value of that volume itself. It's just like these siblings. Effectively, each image is kind of really close to its neighbors in terms of like it's got artificial correlations that are in there. So what you want to do is, if you want, you have to be careful when you're doing cross-validation that you leave out a block that's like covers a fully correlated, like you want to avoid any correlation sort of like leaking between your training and test. That's basically the idea. So I don't understand. The effect of cross-validation on the performance of the model. Well, this is a way of assessing the performance of the model, right? So one thing that cross-validation can help with, so you could just split your data in half, train and test, job done. The problem then is you've like only used half your data to evaluate your model, like because you trained on only half of it. So if you do cross-validation, then it means you get to use a lot more of your data, because you can like use all but one point and just do that repeatedly. So in effect, that can improve the performance of your model because you are using more data, right? So in this case, if I took out half the children, the chances are the model wouldn't do as well, just because it hasn't got as much data to work with, right? So the more clear, like typically more data is better. For like your model will usually do slightly better if you have more training data. If you've got absolutely ludicrous amounts of data, then maybe you don't need to worry. But yeah, right. Did that answer the question? Maybe I misunderstood the question. I don't know. Yeah, if you want to explain more about your question, go ahead. Yeah, right. So I'm doing a detour to linear regression just because the problem's kind of similar and the maths is easier. So I thought it would be best. So we had like this line, and in logistic regression, there's effectively you've got an equation that sort of describes, actually it's in the orthogonal direction, but like like this equation kind of describes the line, right? And everyone recognizes this. You've got some gradient and an offset, okay? So we want to try to find this gradient and offset values for linear regression. And the same can apply for logistic regression, and we can sort of like, typo, sorry, and we can like more complex classifiers as well. Okay, so how do we find M and C? Okay, so we need to do some differentiation. So I've got sort of quickly scribbled out this earlier just to try to like explain this. So apologies if this doesn't really make sense. So we just switched to linear regression. Okay, so we're not doing classification, we're just regression. How many of you actually already know the answer to this? How do you, maybe you already know this, so I just don't need to do this, but how do you know what, if you're just doing linear regression, what M and C are in like, so I call it W there because never mind, what M and C are in this, if you're just doing linear regression, do you know how to infer M and C? So in this case, we've got some points, and like M should be probably like a half, so I mean, because it goes up 1 and goes across by 2, and so on. And then C should be like 1.5 because it crosses the y-axis at 1.5. Does that make sense? So if the correct line would do that. use normal equations. Cool. So you guys have already been taught like the equations that you need. Cool. Have you derived those equations? I don't know whether it doesn't really matter too much, but I'm just curious. I'll assume not, because some of you might not have done. So, right. The cool thing is, rather than the pain of like trying to, it's a lot easier to do this with matrix notation. So I convert it all to matrices. So we're doing linear regression. So what we're trying to do is just trying to find a straight line that will fit these points. Okay, so super simple problem. We can write this down in vectors and matrices. So our y values are like y2, 3, and 4. And our x values are like 1, 3, and 5. Okay, 1, 3, and 5. And we add this extra column here of ones that will allow us to like have the offset. Okay, so we can write down this to sort of explain this problem. Okay. And then we've got a w that we want to choose. Okay, so this is like, this specifies the gradient and the offset. Okay, so if they're both ones, then you end up with this dotted line here. Okay, does that make sense? Yeah, cool. Okay, good. Everyone's already done it. Okay, I'll skip through it really quickly then. So we need to be able to like find the right values of w to like fit this to fit these points. So this is the ordinary OLS, ordinary least square. I guess, yeah. So this is where the least squares comes in. So we have a cost function, okay, that says how good or bad the fit is. So what we do is we just compare the value in y with our prediction. So our prediction is x times w. Okay, so if you look at this, if we have like our prediction for each of these values is going to be this thing times w. Okay, so this lets us like make our prediction. So 1 does that work? So 1 times 1 is 1 plus 3 times 1 is 3. So that's 4 if you add them together, and that's there. Okay, so that's like x times w gives you this dotted line. So yeah, we've got this little example, and this computes the error, as it were, for each of our points. Okay, so you can see the error there is 0, the error here is 1, and the error here is 2, which is what this is, 0, 1, 2. So the least squares thing is like where you square them, and there's reasons which I won't go into about why we use a square operation, and we add them up, and we get an error of 5. Okay, so that's great. We can now we can come out with like a thing, and we want to minimize this, right? Because when we minimize this, it means we fit better the data. Okay. So we've got this cost, and this is how we can write it. So we want to square this number, okay, all of these numbers, and add them together. And you can write that as one equation like this. So this is like the actual values minus our predictions, basically times itself, which is the same as squaring something, right? And writing it like this means you end up like multiplying it, squaring them, and then adding them together. Okay, so it doesn't matter too much about the details, but that's a way of like, this is like our error, and we're timesing it by our error, and so we get the sum squared error is kind of the cost. So we want to minimize the cost, and I'm sure you will remember from school the way to, if you want to minimize the cost, you differentiate it and set to 0. Okay, so the derivative of cost with respect to w, you can work it out. So if you differentiate this, you get this. Set it to equal to 0. We want to solve for w, right? So we do some faffy rearranging, blah, 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 and I won't go into the details. You end up with this expression, which you probably recognize, which gives you your w's. Okay, so that was nice and simple for linear regression. Okay, here's like a little example. Now the problem is that a lot of problems like logistic regression, you can't write, you can't rearrange this step here. This bit isn't possible. You don't end up with a closed form solution here. Okay, so we kind of get to a sort of dead end here. Right, you can differentiate, and then that's as far as you can get. You can put it equal to 0, but there's no way of like rearranging the equation to say w equals something, right? So how do we deal with that? Actually, I didn't explain it in the talk. Oops, sorry guys. I think it's in the notebook. So what you end up having to do is you effectively can, if you can differentiate it still, then you can still find out a gradient that gives you the direction that the cost changes in with respect to w. And then you simply have to just adjust w to minimize your cost by basically going down that gradient. Okay. So you could solve this. Oh, that's right, I had a notebook to go with this, but I don't think I've got time to to use it. So I'm just going to quickly hand wave and just explain it. Like you can effectively find the value of W slowly by rather than setting it equal to 0 like this, just finding that gradient and then adjusting W by that gradient. Okay, and as you subtract the gradient from it each time, you'll end up with the cost going down and down and down until eventually you reach 0, or like wherever the lowest cost is. So that basically, this is the ideal world where you can do it in a closed form step, but for a lot of problems, most of them you don't get to do that. So with logistic regression, you won't be able to write it like this and set it equal to 0, but you can still optimize your weights, your W, to minimize your cost. Okay. So let's just have I'll get back to that in a minute. Sorry, I meant to have a notebook to go with it, but I sort of didn't realize that was necessary. Right, so the machine learning can do classification, we need training data, and we need to decide on features. We need to decide on algorithms, that was a k-nearest neighbors or logistic regression or whatever. And we need to test and validate the method. So really quickly, detouring, we'll get back to that maths in a minute. So another example, when I was in Kampala, some students came to me with a project where they were trying to classify which cells are sickle cell from microscope slides of red blood cells. And they had some pictures of like red blood cells that are healthy and pictures of red blood cells are sickle. And the question is, which one is like, can you count how many are like this and how many are like this? And the problem is that like at this point, this sort of like approach becomes a bit more tricky. You can't just like, you aren't just given like useful features from these pictures straight away. You can do lots of things like measure the circumference automatically, maybe measure the color, maybe the area, you know, maybe the sharpness of any corners or something maybe, and you could come up with a bunch of like features that maybe will help distinguish the two types of cell. And yeah, that works quite well, and there's a lot of reason to do that, especially in where you've only got a small amount of data. That might be the only thing you can do. So with the bees, for instance, we only had a few hundred, right, 200 or 300 true positives and a few thousand true negatives. So we didn't have a lot of training data, not enough for like a deep convolutional neural net. So instead we sort of picked out key features like the brightness of the center, the like how round the dot was, and so on. And we used those features in our classifier rather than like just relying on a convolutional neural net. But trying to pick out features like that is quite hard and typically isn't very successful, like compared to if you have the data compared to a deep network. So yeah, there's lots of possible features. So I think called a neural network or deep convolutional neural network sort of is effectively deciding on the features itself. Okay, but the problem is it needs a lot more data. Okay, and it needs a lot of training data. So we don't really need to worry too much. But the point was, the reason why I went down that maths line earlier is just like this, trying to fit the parameters to the regression line. We're doing exactly the same. A deep convolutional neural network has lots and lots and lots of parameters, and training it involves basically looking at the showing lots of pictures, looking at the output, like assigning a cost to the output, like how good it is or how bad it is, and then differentiating all of the parameters, that output with respect to all of the parameters, and then adjusting all those parameters a little bit by that gradient, and then repeating. And that's basically, so you can see it's very similar in some ways to just standard old linear regression or logistic regression, where you have an equation with some parameters you don't know and you want to optimize them. Oh man, that's a huge topic that one I'm not particularly expert in, to be honest. I don't use convolutional neural networks that much in my research, and two, I suspect doesn't have an answer. I could ask you what you mean by, like, I'll spin the question around. What's the definition of limitation in this case? So, I mean, okay, I'm not going to even answer that question because I don't even know the answer, and I don't know whether there's an answer. I guess we don't know yet, like how far it can go. and there's a lot of loads of augmentation that can help improve networks further. So, but it's not my area, and it's such a huge field that I'm not confident to answer. I'm really sorry. Is that a cop-out? Yeah, no, I'm not even sure how good they are, what the current state of the art is, because every year they get better. So the main limitation in practice for a lot of problems is going to be availability of training data. So from a practical point of view, many object recognition problems probably can be solved by them if you have sufficient training data yet. But yeah, that's going to be the big limitation. So I'm hoping in the autumn there's a couple of students who are starting a project trying to classify videos of bumblebees taken with mobile phones, if you can classify which species they are. And the main concern I had with that project is making sure they have access to sufficiently large data sets of labeled bumblebee images to be able to actually do the classification. So that's that's probably the biggest problem. That's probably the biggest limitation. I don't think that's quite what you meant, but typically it is in real life. The other limitation is maybe more not necessarily about this accuracy, but knowing what on earth it's doing. Right. So back to that problem with the adversarial examples, it's still there's still discussion about why that's happening, and there's obviously a lot of literature on how to avoid it, and so that feels like maybe a big limitation as well. Basically, we don't really quite know. People are doing quite a lot of interesting research into learning what each layer is doing, but it's not completely transparent, right? It's not obvious what is going on. So this was from XKCD, where literally what we've just talked about. So you pull your data in, you look at the answers, and if the answers are wrong, then you basically adjust all your weights, and you go down the gradient until the answers are more what you wanted, right? So really necessarily know exactly what's going on. It's probably a bit harsh. I'm sure the people in the field know a bit more than I do. But anyway, the other problem is confidence. How confident are you of your classification accuracy? So this is quite a big problem as well. If you have, what's an example? So from the dialysis project again, one reason why the clinician came to us is because he wants to be able to assess the confidence of the machine learning algorithm. So if a patient is classified as needing an additional session of dialysis, then that's fine. The problem we have, the problem that's important is you don't want the computer to be overconfident. If there's a patient that's quite an unusual patient, say they're in a different age category than most of the others, or has a particular comorbidity that the others don't have, then the computer might not have any training data that's anything like that patient. But the problem is often deep neural networks or other classifiers often are overconfident and will say, yes, this patient is fine, they don't need dialysis. And what you really want is you want your algorithm to be don't know. And then it can be pushed back to the clinician who can maybe do another test, or back to the point that people had earlier about uncertainty. If you are uncertain about something, then you can look at the risks of inaction and the risk of action and sort of combine that with your uncertainty, and then you can sort of use that to make the decision. Okay. So overconfidence is maybe a problem. And the problem with a lot of data. So sort of our research group in Sheffield maybe worries a lot about coming up with methods that sort of use less data and do it with uncertainty quantified. Oh, quick detour. So I quickly tacked this in at the end. ROC curve. I don't know how many people have heard of it, but it's just an important little feature that you maybe need to know about. So sorry, I'm just jumping around now, but really quickly. This is a really simple example where we're just using the MUAC, the upper arm circumference, to classify those children that we saw earlier. Okay. We've got the ones down here that need treatment, and we've got the ones up here that don't need treatment. In this case, we just get to choose one threshold, okay, like this one. All the children that are under this threshold get treatment, okay? If we do that, it's great because all the children that needed treatment will get treated, okay? So that's fantastic. But we are also treating all of these children that didn't need treatment, okay? But and you can plot that on a thing called the ROC curve, okay? So along the x-axis is the proportion of children who don't need treatment who got it, okay? So it's like the false positives, right? So 80% of the children that didn't need it, all of these, still got treated. So that's why we're at 0.8. Okay. Proportion of children who need treatment who got it. Okay, so that's a true positive. So that's good because all the children that need treatment got it. So we could go the other extreme. So I've just drawn the diagram down here and just treat just the children, like just put the boundary here and only treat these children here. Okay, so that's very efficient from the hospital's point of view. We haven't treated any children who didn't need treatment. Okay? But the problem is we also didn't treat all these children who did need treatment. Okay, so we can plot that on here as well. So it's like the proportion of children who don't need treatment who got it. So the false positive rate is 0. That's good. But unfortunately, the true positive rate is only like 0.25. So only 25% of the children needed treatment got it. Okay. Maybe we could go in between and we plot that here. Okay. So this is like a decision boundary in the middle. You could keep plotting these points until eventually you end up with like a curve. Okay. This is the ROC curve. Oh, feature engineering. Okay. Let me just finish whittering about this and then I'll talk to you about that. So the ROC curve is often used to compare classifiers. So it lets you like assess like classifiers in a way that sort of doesn't worry about what that decision point was for each one. And the other thing we often report is the area under the curve. Okay, so if this line went all the way up to here and then all the way along here, that'll be the perfect classifier because it means that at this point, no children who don't need treatment would get it, and all the children who do need it would get it. Okay, so and this line here is chance. So if you just flipped a coin every time a child came in, then you'd probably get struck off because that would be like seriously dubious like clinical practice. But anyway, if you did flip a coin every time a child came, you'd be along this line because like they wouldn't like that's basically the chance line. So you're just as likely to treat a child regardless of whether they actually like needed treatment. And then usually a classifier is going to be in between these two. Okay? So you can and you sort of the area under that curve is a way of like assessing those two classifiers. Okay? So just something just to like touch on, just so you'll hear about ROC curves in the future probably. So just to feature engineering. So this is about the earlier stuff really. So if you're trying to like classify these cells between these ones that are sort of like healthy and these ones that are sickle, you might do some feature engineering. So that would be like picking out features that are like handcrafted effectively. So or in my case with the bumblebees, it was like I just had some raw images and I picked out particular features from those images, like how circular the blob is in the middle, or how bright the blob is, what the average pick to the center. You know, that sort of like heuristic kind of hacky feature that often does a good job, like and especially you might need it, you might have to do that if you don't have a lot of training data. So yeah, and with the children, in that case, it was like they've used the Z score. So you could use their weight, right? But their weight by itself is probably confounded by their age, for instance, right? So it doesn't make sense just to, if a child's under 7 kilos, then they need nutrition. Like that doesn't make sense because clearly, like when children are born, they're smaller, right? So what you want to do is you want to like be a bit more intelligent, and that's what feature engineering is, where you're like adjusting your features to help your classifier like make the right decision. Right? So, you know, does that make sense? So you apply it, and even when you're using deep convolution on your net, you might still do some pre-processing on your images to like maybe like try to like, although it should be able to cope with scale invariance. Maybe if you want to, you could scale your images, or you could segment them in a particular way. You know, there's various things you might want to do even for like a complicated classifier. Does that answer the question? I don't know. Do you have a particular example, Okal, that you're thinking of? Hello? Anyway, yeah, get back to me maybe with like a particular example maybe that you're thinking of, and we could maybe reason about that. Right, so ROC, we've done. Okay, so we're basically done now. So we've had a look at like all these different, like we haven't really covered a lot of different classifiers, but we sort of looked at some of the tools around classification. Okay, and finally, the cool thing is just more generally about machine learning is you can combine it with lots of other areas. So there's a research project at the moment that's looking at the air pollution and trying to combine it with like the sort of really in a sort of like physical way with the weather. So if the wind's blowing in a particular direction at a particular speed, you'd have some belief about what you think will happen to the actual flow of air pollution over the city. And at bigger scales, people do that with models of the climate and the weather. So we have physical models that describe, you know, literally like the physics of the atmosphere, but you can combine that with machine learning, sort of improve the quality of your weather forecasting. So that's quite a common approach. You can also combine it with control theory. So Boston Dynamics have done this very successfully with their robots, to like combine both like a physics model and then a control theory approach with machine learning on top. So to summarize then, classifiers, oh yes, is an important point. So they can only recognize what it's been trained on. They can fail in new situations as well. So if that example, toy example of the malnutrition unit, supposing we tried redeploying it in a different country, would the same classifier work in a different area or a different region? It can also, they can be overconfident, so that's something we need to worry about. And some classifiers need a lot of data. Okay, so can we be more efficient with our data use? Cool. So yeah, thanks very much. Hope that, sorry, it's a bit of a random collection of topics. I just thought there's like a lot of separate little topics that needed to be mentioned there. So I might have just confused everyone, but hopefully there's some useful stuff amongst all that you found helpful. Are there any questions? I'll just get the notebook. Wow, what's going on? I'll just send you all a link to the notebook that we'll have a look at next. Yeah, so feel free to ask questions. I'm just pasting the link. Okay, so the next, how to make that into an actual link? I don't know, it's annoying. Anyway, this is a notebook that sort of had quickly developed for this. I've just left gaps for you guys to fill in sort of like your answers. Yeah, it's quite long, so probably won't get a chance to get through very much of this today. But we go through a few different, it goes through a few different things. First of all, we have a quick look at implementing like nearest neighbors by ourselves, just to like get some intuition about what we're doing. And then we will then use sklearn, which is like the standard toolkit for doing sort of fairly basic machine classification. Okay, so this is like a really good toolbox of regression classification. It has lots of different methods in it. It's like the de facto standard really for Python users. And then we'll go through some examples. The digit data set is quite famous. I'm trying to remember what else we do. We have a look at cross-validation. We go back to the nutrition example. Yeah, so, and you get to play with all different classifiers and sort of understand maybe some of the parameters and things. So there's quite a lot here. I'm not sure where to start, but I feel like the best thing is for maybe you all to like start having a look at the notebook yourselves. You should be able to, if you go to that link, and then you should be able to go to, so you might need a Google account. That's the only thing. So I don't know whether that's already been talked about earlier. You can obviously you can download the notebook as well and run it on your own Jupyter notebook on your own computer if you don't have a Google account. And if you do have a Google account and you want to use it, just choose save a copy in Drive, and that'll let you edit it because you need your own copy if you want to edit it. Cool. Okay, wow. Okay, right, yeah, these are completely different things. So clustering is an example of a unsupervised machine learning approach where you don't have labels. Well, there are versions of clustering where some do have labels, but anyway, right, we'll just like simplify it. Basically, clustering is where you have an unlabeled, unsupervised machine learning technique where you want to like find like the clues in the name, right? You want to find clusters in your data, right? So if you go back to that the children example, imagine if they weren't labeled, right, and you just had a load of children, and you suspected that there was like some sort of like structure in there where the children consisted of 2 different groups. And it might be that, I don't know if they really work, but you could do k-nearest neighbors or something. I'm just wondering, sorry, not k-nearest neighbors, k-nearest clustering or something, it probably wouldn't work. But there might be a clustering approach that would end up, so imagine if you didn't know these labels, and they're just dots, they might be able to distinguish that there's 2 clusters of people here, right? I'm not sure whether it would work, but that's like an example where you've got clustering, where you don't know the labels, but you're still trying to find a structure in the data. Classification is different. That's where you have labeled data. So that's where you know what each training point is, right? So in this case, we know the value for each one of these. We know this is a treatment not required, not required, 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 and so on. And then classification is where you're trying to then, for a new test point, you want to be able to say which class that test point's in. Okay. I guess with clustering, eventually you might want to know for a new test point what cluster it's in. But the difference is, clustering, you don't have any labeled information. You might not even know how many classes there are. So you might not even know how many clusters you're trying to actually cluster. Yeah. Does that help? Cool. Has anyone had a chance yet to open the notebook? I don't know how to make it into a link. Maybe good. I don't think that HTML works in here, does it? Well, you have to copy and paste it. Yeah. Oh, good. Someone has. Yeah. Brilliant. Oh, good. Okay. Cool. So if you guys want to get started, just sort of going through the notebook, that would be great. Yeah, and basically, as you go through, you'll probably get questions or you'll get stuck on things. So I've got another notebook with the answers on that I'll put out in like half an hour, so you can go through and see the answers. But yeah, if you like, I'll just be lurking, and if you guys want to like ask questions, then feel free. Yeah, and if you can't run the notebook, let me know as well, and we can have a look at debugging it. Are there any other questions?
Thank you, Mike. I think there's a question in the Q&A.
Yeah, this is one. I think this might be the one I answered earlier, maybe sort of. So if you have if you just have 2-fold cross-validation, you're kind of like using half your data for training and half for test each time, which means your classifier doesn't have access to as much data as if you did like 10-fold cross-validation. So your classifier is going to do a bit better if you have like more folds, right? But it takes longer. So the more folds, the more data you get as training data, but the longer it takes. So, but the better your classifier will do. Yeah, does that answer the question? Hopefully, I'm probably supposed to answer it with one of these buttons, but never mind. I'll stop sharing my screen now. Right, is that working? Hopefully, I'm still here.
Okay, thank you, Mike, for
Cool,
the
yeah.
presentation. Yeah, so I think we're all working in our notebooks. If we have any questions, please feel free to put them in the chat and the Q&A, for any help as we work through our notebooks. And I realize we only have 30 minutes to the end of this session, then we take a break. Mike, so
Yeah,
I think
that's fine. It's okay, because this notebook could take quite longer, so it's just for them to get everyone to get started, I guess, and then and later on, if you want to send me, you can ask me questions after the talk and stuff as well, right? So if there's any more questions about the notebook and things, then I'm happy to like hopefully help with that during the week.
Yes, there's a question, Mike, in the chat.
Oh yeah, cool. Don't have control of the features of training. Well, yeah, well, we kind of, so there might be ways of like, doesn't make ML better. So the problem of sort of it picking the sort of like, you can help it with the features. So you might end up always scaling and rotating your objects so they're the same, like have the same orientation and size. and that can help. I know in theory it shouldn't matter, but in practice, there's a limit to how like scale invariant it can be and things. So you can do some feature manipulation at the beginning, and also maybe you want to just like, if some images are really dark and really bright, you might want to normalize the brightness and stuff like that. So there is some faffing about with features you want to do as well. It's not really features, but pre-processing. So the reason why it can make it better is because it can like really tweak and improve that sort of like exactly which features it would find most useful for classifying images. But the problem is, because it takes so much data to do that, you often will find it won't work, right? So it really depends on what you're doing, right? So there isn't really a one answer to any particular data set. That feels like a cop-out. So sometimes it's better, sometimes it's worse. So yeah, back to my B example, because I only had a few hundred data points, there's no way a convolutional neural network would stand a chance, right? You just can't. You wouldn't be able to train that. Like, the problem with it is there's so many parameters in there that you need a lot of data to make sure you have fitted them all properly. There's a bunch of ways of dealing with this. So often people will take one network that's been trained. Say for my Bumblebee classifier, I haven't actually done this yet, but this is my plan, is I'll take a classifier that's already been trained on lots and lots of natural images. Okay, so this means the convolutional layer is already really like well sort of like developed for natural images, right? It's got it's already doing a good job, right? And even layers are higher, like further up, and then I'll basically just take off the top layers and then retrain those with the Bumblebee images, right? So that way you don't need as many images as you would if you were starting from scratch, because the network has already like been pre-trained. Does that make sense? So a lot of the parameters have already been sort of chosen for you using sort of natural images anyway. And the cool thing is natural images pretty well all have the same sort of features at low level, and that's the features that we're talking about. So the ones it learns at the convolutional layer are things like edges and you know, that sort of stuff, right? You know, like the sort of like the really basic building blocks that make up an image. Okay. Does that? I don't feel like I've answered the question though. Okay, I don't know if that answered it. It depends on your data. That's usually the answer to most of these questions. So everyone okay with the notebook? Is that working? Hopefully.
Yeah, if there are any problems, just put them in the chat.
I guess no messages are good messages.
Yes, yeah, that's a good one. Andrew is requesting that you talk a little bit more about hypothesis testing.
Oh, wow. Is there a particular question?
In the Q&A.
Ah, yes, there is. Cool, thanks.
Okay.
Oops.
Yeah.
I have to press the button. Give me a second. Sorry, I accidentally shared my screen. Okay, right. Hypothesis testing. Okay, this is like, feels like a different question. So I don't really know exactly. Maybe you need to be more specific. Is this in reference to like how does it compare to classification, or I'm just trying to think what this means. I'm really stuck on what you mean exactly. Sorry. Like I can explain what hypothesis testing is, I guess. Like normally you have like a null hypothesis, and you've got like I don't know. Do you have a particular question, maybe, Andrew, on what you like a particular application or something? Sorry, that's a bit of a rubbish answer, but I'm just a bit confused what you mean exactly. Is there a bit more? Maybe I need like to know what context you're talking about. Yeah. Okay. So I guess you can look at classification as like hypothesis testing to an extent. So one approach, especially in the probabilistic areas, like looking at the like likelihood of different classes given your training data, right? So you can end up doing like with what's it called? naive Bayes, for instance, is kind of like a really simple example where you might you're almost comparing two hypotheses, and sort of comparing their log marginals and seeing which ones, log posteriors, and seeing which one's most likely. That's kind of like connected to hypothesis testing. I don't know. There's like from the normal, what's it called? Frequentist approach to hypothesis testing though isn't that related, so I'm not sure like it's really connected to classification, and I don't know whether I can start. I don't know whether I would trust myself to start explaining like frequentist hypothesis testing like right now without like a few minutes refreshing myself, to be honest, like p-values and things. Sorry, that's not really the answer you're after. Maybe if you want to be more specific, maybe is there a particular problem that you have that requires it? Or I don't know. Joyce, do you have any thoughts? What any comments on hypothesis testing?
I think, Andrew, it could be good if you could be a little bit clearer in terms of the domain or what particular, because that's really more hypothetical. I'm not answering your question either. Yeah, it's a high level. Because what comes to mind are the p-values, but particularly for what? Because we could also just talk about it from a statistical and probability angle as well. Yeah,
that's true. I'm kind of taking a comfort. There's lots of questions and people saying problems with their notebook. That's a good sign, I guess. I'll be interested to know how far have people got. Which question are people on, or which exercise? I mean, everyone's probably too busy typing on their notebooks to answer. So I don't know. There's. Yeah. I was going to go through the notebook, but actually I think maybe it's not really necessary. I'll just post the answers at the end, and then people can sort of go through. I've tried to explain all of the stuff in the answers themselves anyway, so hopefully there won't be too much extra. So I'm just checking. I'm just going through my notebook now as well, worrying what I've done wrong.
Okay, I think Venon, you've been allowed to speak. You said you have a question regarding image argumentation. Maybe you can speak and then we can move on to the other questions.
Cool.
Good morning, Michael. Can you hear me?
Yeah, brilliant. Yeah.
I just wanted to know, like, if you are training a deep learning model and you don't have a sufficient amount of training samples, if you perform image augmentation, you would get more samples, right?
Yeah.
But you'd be distorting your original data. Because, for example, the domain I'm talking about specifically is potholes. So I'm training a pothole classifier, but then if I'm collecting its sizes as well. So if I use image augmentation on the training data, won't that confuse my model in a sense? Because now the original image and the augmented image both have the same dimensions. So
yeah, I guess I mean this is always the downside of augmentation is you're risking your ability to generalize by doing that. But on the other hand, it's typically shown to work really help quite a lot. So there's only so much. The problem is that convolutional neural nets now are quite good at dealing with things like rotation invariance and things. So there's but yeah, you could definitely, the rotation augmentation I guess would be still really useful for it maybe. I'm trying to think. Also, where are you getting your data from, by the way? Are you collecting it yourself, or is that from?
Yes, I'm cycling around on my bike and taking pictures and a square for the area.
Project. I love it so much. I really love it. Okay, one thing. This is a thing I'm trying out with this is my plan with the bees. So I'll do that. I'll talk about that because I know a little and I should warn you, I haven't really used convolutional neural nets that much. The classification I've dealt with is using Gaussian processes and things. So it's a completely different story, and it's not images and stuff. So I'm starting out in this world of object recognition as well, to be honest. But one thing I've noticed is in the literature for like wildlife classification, almost every single paper I've seen is on single images, and that's fine. But with bumblebees, for instance, it's almost impossible for humans to confidently classify bumblebees from single photos, and that's because you sort of need to see them from different angles to like classify them like correctly, because you need to be able to see whether they've got pollen baskets or whether their noses, like whether their faces are long and all sorts of things. And in general, like single photos just don't contain very much compared to a video. So I'm going to be using videos to like and classify a video. So the idea is each frame of the video is going to get classified, and I'll sort of will combine those together. But what I was thinking about for you is if you're collecting the data, can you collect videos of the potholes? This might be a bit hard work, but then you've got yourself like augmented data kind of for free, right? Because you'll have like, you could pick 10 frames out of each video of the same pothole, if you mean. And then you've got, I know it's not quite as good as 10 different potholes, but you've still got kind of like quite nicely like varying pictures, right? That is going to sort of like really give you a lot more training data, right? So I know it's not as good as going to visit 10 different potholes, but as a trade-off of like the extra effort, you know, it sort of makes sense. Is that an idea? I don't know, I'm sort of just cheating here. One way about the classification is like just collect more data. So yeah, I don't know
That's a pretty awesome idea, because I was actually stuck because the collection takes a lot of time, because I got to take the photo to get the GPS coordinate, and then I got to measure the depth and the area. So yeah, I'll take it into account. Thank you.
You probably already are doing it, to be honest. I guess you're already probably taking multiple photos, but I don't know. That's like maybe that's sufficient then. I don't know. Yeah, it's tough. Like, yeah, the rotated. Like, see what you mean about there aren't that many ways to augment it, really. I mean, yeah, in a realistic way. That's frustrating. That's a cool project, though. I like it. Which city are you in? Sorry.
I'm in Johannesburg.
Ah, right. Okay. Yeah. I'm trying to remember. Were there potholes there? Anyway, yeah. I was there like 2013, I think, a long time ago. I can't remember what the roads are like. They seem pretty smooth. I don't know. Anyway, good stuff. I'll be interested to hear that goes. And you want to do more than just classification, and by the sounds of it, you actually want to assess the depth. Did you say, or something?
I actually want to train a multitask model, so it's got to predict the depth, the surface area, and the severity of the pothole, given an image of the pothole.
Brilliant. Oh, that's really fantastic. Oh, cool. Okay, no, I'd love to hear how that goes. Are you still like in data collection phase, or are you starting to try classifiers?
I only have like 14 to 20 samples, so I'm just playing around with what I can do with it. Maybe some edge detection or stuff.
Yeah, this might be a thing where you maybe need to have like, because the training set's quite small, you might end up having to do feature, like some sort of like feature engineering. Trying to think what you can, what else you can do. It's quite tough. Can you do it by eye, do you think? Just out of interest. Sorry, it's always like interesting, like gives an impression of how hard or easy something is going to be. Can a human, how good is a human at it?
No, I don't think a human would be able to look at it and see the depth. Maybe the severity and the surface area, but the depth is a different one. Because
maybe that's where a video would be really good, because then you get parallax kind of coming in there. Effectively, it's like, or two photos of the same pothole, then that gives you like depth perception, right? You know what I mean? Like, without that, it might be really hard for the classifier to know. Like, it might just be a picture of a pothole stuck on the road, right? I don't know. Yeah. That's quite extreme. Yeah, that's cool. Yeah, no, I'm not sure whether I was very helpful there, but it
was very helpful indeed.
I don't know. Oh, right. I'd be interested. If you have any more thoughts, let me know. I'm really interested in that.
Okay.
Cool. No, good stuff. Oh, see. Oh, cool. Is this a question? How do I identify the test point, e.g. z-score -1 in this case? Willis. Okay, cool.
Question, yes.
Yeah, is that from the notebook somewhere? I guess z-score -1. Oh, okay. So I was just using an example. So I'm just having a look back at the code to see what I did. Test. Where did my training data go? hopefully my training data did include, yeah, cool. So all I did is that thing where I use Z score -1 is I just picked the last point as a test point. Like it wasn't, like ideally with cross validation. So if this was cross validation, you then have a big loop, and you'd pick out from 0 to n each of the Z scores, as it were, or all the training points, like all the different training features, one after the other, and then train your classifier and then test it on those held out data points. But in this case, I did just grab the last one. It was just that first bit's just like a quick demonstration of like k nearest neighbor is just nearest neighbor, I think, one nearest neighbor. So I just picked a random point. It wasn't for a reason, really. I could have picked the first one rather than the last one. Is that sorry, it's a bit lame. There wasn't any deep good reason for it. It was just and the -1 means the last is the way Python writes the last item. So I could have used Z score 0 instead. Yeah, but then I'd have to have been careful. I'd have to have rewritten my the code. So let me just share my screen actually. 1 second. Share the screen. Okay, cool. So hopefully this still runs. This should run. Right, so it's this line here you're concerned about. Why on earth did I pick -1? So I could have chosen 0 for these, I guess. Run, and then here I'd have to be careful not to include the first one. So right, 1 to the end here. Okay, yeah. So yeah, there wasn't a good reason. Hope does that answer the question. I'm just going to undo those changes. I don't know how it was. Cool. Did that answer the question? Hopefully. Oh, cool. Right. Where are we up to? Quick detail on those numbers. Okay, cool. At the top. So I can all the questions as I made. What is the problem with finding this size? Ah, yes. Okay, cool. Does anyone have an answer to exercise, like exercise 0? Let's paste it in here. So yeah, Vernon, I'm thinking more about your problem. I do feel like pictures from different angles will give it the best hope of spotting some sort of depth. Well, you could. There's lots of not machine learning, but lots of algorithms for doing. I think I've seen online for inferring depth from more than one image. So, like, I mean, not depth of plot. I mean, just depth, like depth of the objects in the picture. So maybe it would make sense to like use something like that, and then use that as a feature in your algorithm. So it means that could be like a pre-processing step where you explicitly handle pairs of photos. Maybe maybe you have to take 2 pictures from a meter apart or something, or I don't know. I'm trying to think how you do that in a simple way, and then it can, yeah, I don't know. Maybe you need something like that, like an actual like a what's the word? Yeah, pre-processing step where you worry about depth. Let me just Google it. Any other questions while I'm just looking around? Or yeah, if anyone has any answers to that exercise 0, I'll be interested to hear how people are doing. Oh yeah, most phones do have like 2 cameras on now, don't they? That's new ones anyway. So maybe your phone can give you depth information already, does it? Also, I guess you've got texture information, maybe, I don't know. The problem is the depth that we're talking about is a really small change, isn't it? It's only like, unless the pothole's really bad, you know, compared to like the total distance.
I think, Stefan, you asked a question about the data and the Python code. I've just shared the link to the notebook that we're using. You're just in here. I hope that you can have access to it.
Cool, yeah. So the, let me just find the slides. So the slides, I think they're accessible. So, how do I answer? I'll just answer it in here. So my slides are here. And then the notebook is here. And then I think I might just post the answers as well, just because we haven't got very many minutes. I'm just trying to find the answers. Hopefully it's got the answers in. Let me just check. Cool, okay. Answers. Right, okay, here's the answers to the notebook as well, just because we've got a few minutes left. I don't want anyone to miss out. So maybe I should answer the first question because nobody else did. But the main concern in that really simple case at the beginning, so exercise 0, okay. So what's the problem with finding the distance using just the MUAC and Z-score is that like one of them is like varies over like plus or minus 1 maybe, and one of them varies with like plus or minus 10. Like, so the problem is that like any distance that doesn't use normalized data is going to end up massively using the MUAC data more than the Z-score data. Does that make sense? So you can see it better when you plot it. Anyway, that's a very brief answer, but you'll be able to see it more when you play with it in the notebook. Cool. Yeah, Joyce, so I was just going to ask you actually, just to like chat while people are working on their notebooks. Have you in your projects and things sort of needed classification and what has it been? Have you been able to just use like simple methods from sklearn, or do you find you have to like write your own? Have you used deep convolution on your networks?
Yeah, so the 2 main areas that we've tried to do classification has been for our data sets from agriculture and also the data sets that we have from for malaria diagnosis. So I'll drill on agriculture because that's where we've done most of the work, and health is being done by Rose, who's our PhD student. So our project 1, we began with cassava, where we sent out our farmers and on our network to keep collecting image data and send us this data. And we try to make sure that the data that is sent is as broad as possible in terms of the classes that we require, because the problem that we are going to do or that we've done is a classification problem where we try to, for example, classify cassava leaves as either healthy or diseased, and the diseases have different classes, for example. And the same has also been for beans as well. We have a group of students that have built a model for beans classifier, and so we also ensure that we have as much data as possible for both the healthy class and also for the diseased classes for 2 main bean diseases that we've been trying to focus on for this project. So in terms of the data collection, this really has, if we start from there, it's really been helpful and geared by the farmers that we have on our network to give us these. So after getting these particular images. We've also tried to work very closely with the agricultural experts to really help us in trying to divide up the images that we have received in the different classes to annotate them, either they're diseased or healthy, because we are not the domain experts, they are the domain experts. So we've worked very closely with them to try and help us to do this. And then based on these different classifications, we've been able to train our models. So for most of the methods that we've used methods from sklearn, that's a Python library that we're using in this notebook, and that's the way we've been able to come around with building the classifiers that we have. I hope that provides a very high level overview
really
of what we've been trying to do. Yes, with our
that's really good.
class.
One point you made earlier on, which I wish I'd mentioned in my talk, was the you mentioned about how important it was to get good quality data, right? So, if your training data is really if it's got a lot of problems in it, like lots of wrong labels or lots of poor images, then that can end up messing up the actual classifier, right? So I think you mentioned earlier that how important it was trying to keep that quality high.
Yes, that's important. Yeah, and also we've kind of also tried to be very deliberate, especially with the farmer trainings, and we've really had them trained on how to, take very good images, not rule out that sometimes we don't get bad images, we sometimes do get bad images, but we have to first, try and look through them and see before we take these images that we're using for building the classifiers. So we've tried to be deliberate in that way, because sometimes you get blood images, and also sometimes the farmers also, when they take the images, they can decide to label them. So we've also been able to not only rely on that, but try and especially rely on the experts, because they know which kind of classes that these different images belong to.
Yeah, that's really interesting. Cool. Yeah, getting labeled data can be so hard. It's like the biggest part of the project sometimes. So yeah, that's brilliant. No, it's a really good project. It's good to hear it's still going on and things. Yeah. Sorry, some questions. Can I just quickly skip to them? Do you perhaps have any other augmentation techniques? It's not my expertise. I'm so sorry. I really hopefully some of the people later in the week are more expert at object recognition and image processing and things, who can advise on who can advise a little bit more. I'm really sorry, I can't help more. I think my main hack was just to get more pictures and use those. Taking cells inside of a 3D image. Yeah, that's the thing, is you could try taking it from different angles, but I don't have, it's not an area I know much about, so I'm not sure I don't have in my brain any other techniques that I know of. But if anyone else has any suggestions, feel free to jump in, and I definitely don't, it's not an area I'm particularly expert in, so I'll be happy for other people to suggest ideas. Sorry. Hey, Joyce, there's a question for you. Question not for me, so I leave.
Oh, okay. What kind of image data are you collecting for classification? So we are collecting cassava data and beans data, both in the healthy class and the diseased classes as well. So that's the image data that we are collecting. Yeah,
and to this latest point, yeah, exactly. Take multiple images is what I was sort of thinking that he should do. And the one thing I was kind of thinking though is rather than just feed those in as 2D images, I was Googling around trying to see what methods exist to use 2 images, like the standard stereographic, using the stereo image, like the fact you can see the pothole from 2 different angles means you can infer depth, right? So, and it's probably best to do that in a sort of direct calculation rather than ask the machine learning algorithms to do it. And then you could give that map, that depth map, to the algorithm for it to use, rather than expect it to try to infer the depth from the 2 images. Yeah, no, I think you're right. I think that's really good. I think that's the way to go. Yeah, multiple images. But I can't find I think it's just too many papers where people are trying to do something clever, and I'm not finding a simple way to just. There must just be a Python library probably somewhere where you give it 2 images and it infers depth, because it's not infrared depth from a stereo image isn't exactly too hard. The only problem will be how far apart are the two photos. So, you know, if that's not standardized, then I'm not sure how easy it will be to infer, like, correct that. What other questions are there? I have lots of challenges to get HSI data. I'm working on classification.
Yeah, I think Tagel, you're asking about the hyperspectral data, right? So our data is really phone data that the farmers take. We haven't really gone into collecting that kind of data before. Mike, do you have any thoughts on that, on the hyperspectral?
Oh, I see. I don't know much about it. So hyperspectral data, so is this where you are using like a clever camera that gives you like a detailed like spectrum of every photo? I'm just Googling it as well. So how much, yeah, so I mean, yeah, again, this is quite a domain specific thing that I won't know very much about. How, like what, okay, as a human, forget the actual classifier for now, and as a human, are you able to see whether a crop's diseased or not more from the HSI images? I mean, if you take the white slice, or do you find red, green, blue is sufficient? I mean, so it kind of really depends on this. And actually, maybe Joyce, you might be able to answer this. So presumably there's reasons why I use HSI, and that's probably because there's like maybe even quite narrow notches in the spectrum where a disease might change the image. But I mean, I'm not an expert at crop disease. I don't know what the like what the advantages are. Do you have any? Yeah, I think maybe Joyce, you probably can answer the question yourself more than I can, to be honest. Do you want to jump in?
Yeah, so I think also Godliver is on this call. Godliver, you could also give very useful information. I think we've done a lot of spectrometry data, spectrometry work, sorry, as well, in a way. So because I think it's also very, very important for early disease detection, like Tagil is trying to ask over here. So I'll just unmute your mic for a while. So you could probably share your expertise with him. I hope she's still here.
Really quickly, before, if she's not, but can I just quickly jump in? Yes. Did you see, just, sorry, different topic, back to the potholes. There's a message from Stephanie on the question and answers. Why not make a pothole? You can then control the size and depth. That's brilliant. That's really, really good. I love it so much. You can just like, if you've got a bit of ground, you can like hack at with a, maybe it won't behave quite the same way as a real pothole. That's the problem. But I do quite like the idea, like, you know, of like just, then you could make as many training points as you want. But whether or not it's as realistic as a natural pothole, as it were, and it's in this wild environment, I don't know whether like a homemade pothole is going to have the same features. But it's I like the idea a lot. Anyway, yeah, I'll just make sure I pass that on. I'll paste it into the chat just in case people didn't see the question. Cool. Oh, okay, right.
Yeah, but then also I think Tagel, you're still also really asking about the data collection part of it, because you're saying you have a lot of challenges trying to get this data. Okay, so Godliver is here. So Godliver could share her experience, how she's managed to get such data, cool. and maybe that would be really helpful for Tagel. Godliver, I think talking is permitted for you now. Thank you.
Okay, Joyce, please, could you help me repeat the question? I was a bit off.
Okay, yeah, it's fine. So Tagel is, he says he has a lot of challenges trying to get hyperspectral data. He's working on HSI classification, especially for crop disease early detection of crop diseases. task based on RGB or HSI image data. So he probably needs some advice there around the data collection and how to, a little bit how to work with the data, I suppose. And
Yes,
Tago, feel free to come in and interject if we've not answered you.
question. And yeah, so we've been working with spectral data with crop detection, of course, for early disease detection, working with cassava, and we worked with near infrared spectrometry, the technology. So the hyperspectral, of course, not directly in that line, but maybe could be related, but we haven't experimented with hyperspectral, but I guess it could be something, a study that is related. Yeah, so from our experience, so of course, spectral data is a bit sensitive. We got data from the fields first, and then we tried to bring to make an experiment more controlled. We also went to the greenhouse experiments. So in that line, I guess maybe I'll need to understand more how the experiment is set up. Then I can advise more. Yeah, but in regard to spectral disease detection and spectral analysis, the data is there's some good. There is good hope. Of course, our results were very promising compared to image disease diagnosis. So it's possible we can detect diseases very early compared to using image data. So it will be a good comparison to look at how hyperspectral data works also in that line. Thank you.
Okay, thank you, Godliver. I think again it would be very important if you can get in touch with Godliver for a further clarification here.
Yeah, thank you.
Yes. So I realize we are on top of the hour, and according to our program, we should be taking a break for 30 minutes before we can get into our next session at 12:30 about machine learning systems, which will be given by Neil and Andrea from University of Cambridge. So Mike, if you have any final remarks.
No, that's great. Hey, thanks for hosting this and keeping Data Science Africa going amidst this chaos of the pandemic. No, it's really wonderful to have it going and so many people taking part. It's really wonderful. Cool. And if anyone has any questions, what's the best thing to do? Maybe, is there an email address for what's the best way in the future for them to ask questions? So like every next week or so, if they've got a question for me.
Yeah, so we have a Facebook group. I think we should have mentioned it. Yeah, DSA, where we are all going to interact and ask questions further. So
grand. Okay, I'll go and join that. That's good. Cool.
Yes.
Wonderful. Cool. That's great. Okay, yeah. So if anyone has any questions over the next week, that's probably the best way of contacting me. Yeah, and then I'll keep an eye on that. Yeah, that's fantastic. Wonderful. Cool. Thanks, everyone. Hope you found it useful. And I'll keep. I've got to disappear, but I'll be back for the rest of the essay, like on and off over the week. That's great. Cool. Thank you, everyone. Take care.
Thank you, Mike. Yeah, so we'll take a break. Please don't run away. We'll be back after 30 minutes for our next session. Thank you, everyone.
Hello. Now in the afternoon, we're using a different link. So I'm going to end this, and then I open up another link.
Cool, are we switching over to the other link?
Yes. Oh, Neil. How are you?
I'm good.
Just not to confuse people, since we had created a different link for the afternoon.
Yeah.
It's better we click on that. We use that.
Okay, cool.
Billy is also online. Okay, good.